drag system. We'll then go into our proposed solution, which is an architecture of embedded antennas. And then we will talk about how we executed this solution through altering our composite manufacturing process, integrating these antennas, a control PCB for the ADS, and a LoRa design, as well as the switchboard for the PCB of the ADS, and how all of these systems are integrated into our ADS as a whole. We will then talk about the testing that was done and the results of these testing. So the main root of our problem is our carbon fiber composite architecture. So we have a goal of maximizing how much in-house manufacturing capabilities we have in our carbon fiber composites. So carbon fiber is very strong and light, so we want to extend that as much as we can throughout the rocket. We also have an interest in teaching members of the team about composite manufacturing, as a lot of our processes are very similar to what is done in industry. Currently, the SRAD composite components that we have throughout the rocket are the upper and lower airframe and all of the thrust structure. The only COTS structural components that we have are the nose cone and the couplers. So as we extend our carbon fiber components throughout the rocket, we're limited in our telemetry as carbon fiber is conductive. So any parts of the rocket that are carbon fiber are they act as a Faraday cage and don't let any telemetry out. So our goal is to try to solve this as the ADS, the active drag system, which Kian will talk on more in a second, is in our lower half of the rocket that is surrounded by this carbon fiber. So we need a way to communicate with that.
So this is the active drag system. It is a simple mechanical system that acts as our solution to the IREC altitude accuracy challenge. Our rocket every year is designed to overshoot our 10K altitude target and then use a system of actuated drag flaps that stick out at angles from the side of the rocket to slow down that apogee and ideally hit 10,000 feet. This is the mechanism that does it in its entirety, fully integrated right now, aside from the flaps, one of which is on the table. For stability, it's mounted as low down in the rocket as physically possible. There's a carbon fiber bulkhead that's mounted right on top of our motor tube that the ADS will slide onto these threaded rods on top of, and then once the carbon fiber body tube that you can see in this image in the right as Canon is inserting it onto the rocket is installed onto the rocket, then the flaps will be installed onto the outside. As he said before, this means that there's carbon fiber below the ADS and all around it, and multiple bulkheads and other things up in front of it. We want to get GPS signals into the ADS so that it knows where it is, and we want to get telemetry out of the ADS so that we then know where it is on the ground. But as it's entirely surrounded by carbon fiber, as Cannon said, that is entirely a Faraday cage. We can't get these GPS signals in, and we can't get our telemetry signals out. What we're talking about right now is our solution to this problem, which I will hand off to Brenton to explain.
All right, so since we cannot transmit through the carbon fiber, instead of adding small antennas or bulky shrouds to the side of the rocket, we've decided to implement patch antennas around the rocket for multiple bands. So we have our 433 megahertz band, our 2.4 gigahertz band, which we won't be using during competition due to frequency restrictions on bandwidth, and our main GPS telemetry band. So we've decided to have 4 antennas around the rocket such that we can select which antenna to use based on signal strength, based on the orientation of the rocket. So say the rocket lands in the desert at an angle, but we're transmitting through the bottom antenna. We're not going to get anything. So we want to switch the top antenna such that we can talk to the GPS satellites and get maximum signal integrity.
So as I mentioned, in order to implement this embedded antenna system, we had to make some changes to our composite manufacturing process. So a normal composite tube is wrapped around a 6-inch diameter aluminum mandrel. We have large carbon fiber sheets that we wrap around the mandrel and wet as we go. The tubes are 3 wraps thick, and they are then rotated over a space heater to cure. Once the tube is cured, we do what we call post-processing, which is where you sand the tube and coat it with epoxy to increase the surface finish. So that post-processing step is where we implement the antennas. So we'll normally do 2 or 3 layers of post-processing for the surface finish. In this case, we'll just do 1 so that the antennas have a good surface to connect to. And then we will coat the location where each antenna is with electrical tape so that the antenna is not interfered with the conductive carbon fiber underneath. We'll then put those patch antennas on and thread the leads through the wall of the composite tube. UFL to UFL extensions are then used to extend the wiring of the antennas up through the thrust structure to where the ADS sits forward of the thrust structure. And then this tube that you see there is then implemented into the thrust structure during the full assembly, and all those wires are threaded up through the couplers and the bulkheads that lie within that assembly.
Yeah. So on top of the ADS is the actual control PCB that will be intaking all of these GPS signals and outputting all of our 433 megahertz telemetry signals. It is a relatively complex system that does a variety of different things. It's based around the RP2350 microcontroller, which is at the core of the Raspberry Pi Pico 2 standalone microcontroller. Really good at what it does. It's a dual core processor, and that makes it very nice for handling all of the different math and things that we need to handle during flight. We have a 16 megabyte chip that does flash memory, which we'll use to log all of the data that the flight computer is both collecting from its sensors and calculating for all of its sensor fusion algorithms during flight, in addition to GPS coordinates and all of the other data that we're intaking. That onboard sensor suite includes a mid-G IMU with a gyroscope and accelerometer, a high-G accelerometer that goes to plus or minus 200 Gs, a barometric altimeter, and a 3 degree of freedom magnetometer. So we're getting a decent amount of data that we'd like to then transmit back down to the ground. There's also a decent amount of power and signal isolation circuitry that lets us separate out all of the actuator circuitry that drives the servo that actually makes the ADS do what it does and drive all of its flaps, which you can see down at the bottom left corner with a giant power MOSFET and a couple of optocoupler and diode circuits that let us completely isolate both the power and the signal circuitry of the high voltage servo from the low voltage microcontroller. Most importantly, what all of you are here to listen about is the onboard integrated LoRa handling and GPS handling. You can see the GPS handling down here in the bottom right. It is based on a u-blox Neo M8Q module and has a couple of diodes and its own power regulator to separate it out so that we can then use this USB port on the bottom to debug it separately from the rest of the system if we desire to. And up the left side of the PCB, you can see all of our LoRa handling. We have two separate LoRa systems on this ADS control PCB, one of which we designed and one of which is a commercial module as a backup. This network right here, that's mostly at a 45-degree angle and is labeled really largely LoRa, is the network that Brendan designed that he'll talk more about in a second. And that drop-in footprint up at the top left that's labeled backup 433 LoRa then gets one of these, it's kind of hard to see from me holding it up at the front, but a little green radio module that's based around a separate chip that we have proven on separate breakouts in the event that testing with our onboard LoRa network doesn't go very well.
All right, so the LoRa design, 915 megahertz is in the ISM band. A lot of teams use it. It's very congested. So we decided to go with 433 this year because it's less congested. It requires a ham license, so we expect less users. Also, 433 megahertz, we can transmit further, which is great for our competition. But yeah, so our LoRa design implements Semtech's LR1121, which has a sub-gigahertz path at 22 dBm transmit power. It also can provide 2.4 gigahertz power as a backup, so that's why we use this chip specifically. It required a custom impedance matching and filtering network. So that's why you see all these capacitors and inductors and all this craziness right next to the chip. Big mess, but it's kind of fun. Yeah, so we tested this in LT Spice, tested the filtering network, and make sure it applied with the FCC regulations such that it's attenuating all the harmonics and making sure it complies. We also have the backup 433 transceiver module for redundancy in the events that our onboard hardware, we get difficulties with it or it fails or we burn out a chip or something like that.
So we've talked a decent amount about all of our onboard GPS and LoRa handling, but the keen-eyed among you may have noticed that with this really big fancy control PCB, there is only one SMA port for incoming GPS telemetry and one SMA port for outgoing 433 megahertz telemetry. How do we then select between the 4 different antennas for each of those bands? The answer is an entirely separate PCB, which you can see up here. It has 10 total SMA ports on it, which total about $30. And other than that is literally just a couple of RF switch ICs and level shifters to talk to them. You can see 2 jumpers on the bottom left and bottom right of the control PCB. They are each 4 wires, the one that's red, blue, and black, and red, green, and black. That exists entirely to be power, ground, and 2 select bits for both the GPS and LoRa systems. It is very, very simple. The switchboard PCB is a little bit hard to see on the bottom of here, but I'm going to try to hold it up for you. It will permanently have these 2 jumpers on the side that are just SMA to SMAs for the actual signal connection between the 2 PCBs, and then these 2 4-pin jumpers between the 2 to allow us to select between all of the different signals that we'd like. Most of the time, all of these SMA ports will remain exposed. These SMA connectors will then be installed onto the switchboard during final integration, which we'll talk more about in a moment. This is a much simpler PCB than the control PCB. The switchboard is only 2-layer, the control PCB is 4-layer, and is also significantly larger, as you can tell. For actual integration, as we mentioned a bit ago, the ADS assembly will slide onto these threaded rods once these antenna extensions are removed from them. There are 4 corresponding holes on the bottom of the ADS assembly. There are 4 of them in the direct corners to slide onto these threaded rods, and then 4 slightly larger rectangular holes next to them. That is where we'll pass the 4 different antenna extensions up through, and they roughly line up with where the holes are drilled on the bulkhead for where the ADS will sit. Once the ADS is mounted in place, and we take great care to make sure that none of these cables are pinched up against any nuts, and it's actually sitting flush on all of the mounting bolts on its bottom, we'll then take all of our antenna extensions and pass them up and screw them onto their labeled switchboard connections on the bottom. All of these little bits of purple electrical tape that are on each of the antenna extensions is labeled both with the band that that antenna is connected to and the number of the antenna. You can see these numbers written around the outside. There's a 2 here and a 1, and you can't see the one on the back, obviously, but that's labeled for which corner each of these antennas is, and there are labeled silkscreen numbers on the bottom of the switchboard that we'll use to figure out which antenna goes to which. This is mainly important because we don't want to just randomize which antenna is which. There is a specific direction that the ADS will get mounted inside the rocket, and that means there is a specific direction that is up once it has landed. This allows us to specifically make sure that the direction that is up is the one that we're selecting once we end up on the ground to maximize our GPS telemetry and hopefully receiving our telemetry packets from the LoRa radio.
It's important to note that we've only done ground testing so far. This has not been in flight. It's very experimental. But as far as ground testing goes, very successful. We first test all the patch antennas with our VNA to make sure the resonant frequency was correct so we don't mess anything up there. Saves a headache for the future. But yeah, so our VNA was connected through the switchboard, so we were able to connected through the switchboard to the RF switch functionality for the GPS and LoRa before the actual system test. GPS was defined, it had no huge differences through the switchboard versus directly connected to the GPS module, which is good. And then likewise, when the switchboard was tested with live switching and antennas during the GPS receive LoRa transmit, there were also no significant performance differences. And we're excited to see how it does during flight.
All right, that's all we had. Thank you everybody for your time, and if you have any questions.
So I'm going to process since I'm a test engineer,
Yep.
I am very interested in terms of the validation. You said you only have done ground testing. What does validation for you look like going into your flight? What is a proper success look for?
We're going to go through each individual step of all of the individual pieces of what we're trying to accomplish with the ADS control and switchboard assembly. That means first off, starting with just using the ADS control PCB. We'll use these SMA ports on it directly and plug each one of these antennas into it one by one and ensure individually that we can get GPS telemetry into it. First, just by plugging in a USB connector into the separate connector on the bottom, just so that we can do that bare minimum baseline testing. Then integrating it into the entire system, powering it all on at once, and making sure that the GPS can communicate with the microcontroller itself. And then once we make sure that the antennas themselves and their radio modules are behaving properly, then we connect everything up through the switchboard and make sure that, one, we can switch each antenna respectively. The way that we do that is only connecting one antenna at once and setting the select bits for, okay, which one do I want? Antenna 1, I want antenna 2, etc. And rather than trying to do immediate telemetry reception, we'll first just pass a VNA signal through the switchboard directly to make sure that each port is behaving as we expect it to. Once we make sure that using the VNA, it is behaving exactly as it should without possibly damaging any of our components, then we'll begin actually putting in all of the antennas and bit by bit making sure that each of the antennas individually does what it is supposed to, and then with the microcontroller switching actively with the GPS module actively receiving GPS telemetry. If we switch it while it's doing that, making sure that doesn't interfere with anything. If we do that while our LoRa is trying to transmit, that doesn't interfere with anything, etc. We want to make sure that ideally no active switching should happen while we're transmitting or receiving, but in the event that it does, we want to make sure that nothing gets damaged in that process.
Yeah.
Did you guys notice any significant losses from the length of your cables going through your antennas?
Yes, a little bit. And that's something that we intend to improve on the future. This is the first year that we have fully integrated the system. We tried to do, on our last year's rocket had the ring of 4 antennas and had an idea to do something like the switchboard, and it ended up being entirely too complex for us to integrate at the time, and we mainly focused on the ADS control PCB. Once we got that hardware lined up, then we made the switchboard, made sure that they could communicate properly, and started out with just giving ourselves a little bit of extra leeway on how long all of these cables are, and you can tell they're pretty long. In the future, we do intend to shorten them. That was decided on in testing with our VNA and doing all of our ground testing. There wasn't enough of a noticeable impedance just from how long the cables are to impact performance that much, and we decided that it was better off to just leave the system working as we know it mostly does than try to modify it and improve that performance, as this is an initial test of all of the integrated systems working at once.
Yeah, in the back.
So does switching occur in flight?
If as of right now, no. There are 2 different states that the system will try to use during flight, just to make sure that the switchboard for this year's rocket is behaving at a baseline. In the future, we may try to, like, if the rocket is spinning very slowly, try and use the antenna that's pointing towards our ground station. For right now, there are only 2 states that it will try to do. When the rocket is on the rail, we'll select the antenna that is facing away from the rail so that we're not just blasting telemetry into the gigantic metal object that's next to the rocket. And once it lands on the ground, we'll use the onboard IMU on the ADS control PCB to figure out what way is up, and then select the GPS and telemetry antennas that are facing upwards, and hopefully maximize our chances of receiving GPS telemetry for recovery.
So do you have something for roll control right now?
As of right now, no. We only have our drag control, and we only have 1 actuated degree of freedom per DTEG regulations. So the rocket will spin however fast it does, and only 1 of those antennas will be working at that time.
So I know you guys did a few different test flights, but you said you haven't flight tested this before. Did you just like build a whole new booster for?
So these have been integrated, like just because of our manufacturing timeline. This has been built and this has flown twice with the antennas. They just were not actively working on the on the electrical side.
Okay, so like,
Yeah.
you guys doing any kind of testing in between test flights to make sure everything is still chill after the boosters hit the ground?
In terms of the antenna performance or in terms of the thrust structure performance?
Either.
Yeah.
Well, on a thrust structure side, like we're not kind of altering other than those tiny through holes, we're not really altering the structure that much. So this is a design that we've flight tested multiple times and with multiple test launches. So there's not like a specific process to check the integrity of the thrust structure itself.
And as for the antennas themselves and their extensions, we do try to reinforce them as much as possible. There are 2 separate points in each extension that we clip on a UFL to UFL extension, and obviously that's 2 possible points of failure. If you look a little closely on each of these antenna extensions, you can see a little bit of clear heat shrink. We'll put hot glue on the top of each of those UFL extensions and then crimp heat shrink tubing on top of it to try and reinforce the connection as much as possible. This is a mechanism that we have tried in the past and has worked pretty well, and so far we've seen no problem with it. As for testing the actual system during flight, this is the most complex PCB we've ever produced, and it took a while to draft the different designs for, especially for integrating the GPS and the LoRa onto the PCB. Last year's ADS did have GPS and LoRa capabilities. They were separate breakout boards that were mounted on the underside where the switchboard is now that we just communicated with over standard comms buses. Brendan worked on a previous prototype PCB in the fall that integrated some of these systems and worked on a prototype of the LoRa filtering network, actually on 915 megahertz, so that we could test it on a non-ham band. And we have recently gotten that working and know that the LoRa chip on board works and are working on integrating everything for 433, and we'll be flying with it ideally very soon. So we, in the interest of knowing that these PCBs will be difficult to design and order and produce, have gone through a couple of iterations of prototypes to try and do the design at a simpler level during the development process before ending up at this big integrated system with 2 separate PCBs talking to one another.
How many test flights did you do?
2.
2? Okay.
Yeah, both in the spring.
Out of curiosity, who's the ham on the team? You're the ham?
Yep.
Okay. Is there anything else other than just integrating into your Rocketry? Cool.
Yeah.
Like I have Egg-Ton or Quasar, so that's why I got it.
Okay.
But that's really it.
Yeah.
Any other questions?
How long did the design phase of this PCB take you guys?
You want to talk about Bearman first?
Yeah, sure. So it started with kind of like a tracker board. So we had all the sensors and kind of telemetry on one board, and a lot of that design was implemented, little tweaks here and there onto the control board. So it started probably September, and then all the way up till April, May. So in terms of that actual physical design, it just kept going and going and going. Little tweaks were made here, there, but a lot of the conceptualizing was done in the fall before winter break.
Yeah. The Bearman PCB probably took about like a month and a half to 2 months of like overall just figuring out the design, what we wanted to put on it and test with the prototype. And then the ADS control PCB itself was about another month, counting the switchboard development as well, as both PCBs were developed at the same time in conjunction with one another. Any other questions?
Okay, thank you.
Thank y'all for coming. Yes, sir.
Would you like your two?
Yeah, this is
There you go.
I've gotten really used to gesturing with the ADS.
Let me just.
It's kind of difficult to see.
Let me toss it to you real quick. Alright, I can do that.
Wait, this is one. Daniel.
Good to see you, buddy. Are you getting any more sleep?
Daniel, this is part of. Sorry, this is part of yours too. I took it out before I was doing it.
Oh, yeah. Like literally.
That went a lot better.
I mean, I was asleep by like maybe.
We're all very articulate. Team 44. That's
that's all just waste we're gonna get out of you today.
That's good.
Wow, Daniel just completely the bit just completely went for Daniel's
We were
head.
really just talking about how little food money I have.
Alright, so
Yeah, I came by to talk to them.
We were at the provider.
They can just like get one of these flags.
You said you're coming tomorrow.
yeah, I think we should do that.
These are precious.
Alright, we got 7 minutes.
I didn't care actually.
Where are others?
It's just a line. The other judges are just.
Oh, okay.
Yeah, so
That happened last year too.
it did happen last year.
Good job, Paul.
My voice has been giving out. I'm really surprised it behaved as well as it did there.
What have you been doing?
I was talking very loudly as one of our main people at the table yesterday.
So you're blowing your voice out.
Apparently, right before the podium.
Drink some like honey with some tea in it.
Yeah, we made a Starbucks order this morning, and I got a big thing of tea with honey.
Get this man a warm drink perpetually.
I only need to be able to talk
You're the backup.
I don't need to be able to
You're the one that's supposed to like I'm the one who knows something.
Okay, perfect.
At least you can read. You can read.
Well,
Northwestern, they didn't look at the newest schedule, so they didn't know if they were on it. Do we not finish that? Like, I don't know how to tell you. Like,
No, I'm really proud of these PCBs. They came out really well.
But yeah, you're more than welcome to use this one. You can use your own. It doesn't matter. You can pull the HDMI cord and yeah, okay. That's for the live stream, so they can hear you.
Is it gonna break and
Back to
you
the
go?
table, but
Good to meet you.
nice to meet you.
Hey, Daniel.
And he's like, yeah, it's fine. And he's like, it wasn't fine. It didn't work, but that's what he was doing.
Is this one yours too?
Charles Watson project.
Charles.
Yeah, I'm working at CMAR.
Yeah.
I'm asked to do this.
Daniel told me about that. That's so cool.
So I'm really excited actually because my alternative was going to work for Rowan in California. Fuck that. And also this work is kind of directly related to my personal interests and I think I can do cool shit.
It's gonna be the two of you who are presenting?
Yeah, oh, absolutely.
Is it not wanting to?
I'm happy to. I won't remain in an active capacity because it would be weird for an ex-lead to then just be a member afterwards. But if they want me to like review pieces or like give a seminar or something, I'm absolutely happy to. And I'll hang out with them.
Let me see if these ones to connect to.
Like, hey guys, by the way, can I be a member and just sit on the team? I've got 3 years of RS-25 experience.
Let me see real quick if it'll at least connect. That way I can.
I'm like 90%.
I'm trying to determine if it's a laptop or.
I got a judgment piece. Did a really good job.
You did see the HDMI screen on the PC?
I'm gonna go head out and meet Cosmo, but I'll catch up again in a minute, Lonnie.
Okay.
Immediate just voice cracks.
Abbiamo una concorrenza un po' troppo forte, mi sembra che stanno tutti di là. Quell'altra.
I'll be right back. I'm gonna get the pen for this in case you need to open it here.
Yeah, thank you.
So you'll have about 4 minutes to get set up and started. We'll have the 25-minute timer on the back. If you finish early, you can start taking questions early. If not, you'll have the 25, and then we'll do about 5 minutes of question and answer. Okay. So let's just see if we can get it pulled up. I was working on this laptop, so I'm not sure if you have a USB. Oh, okay. There we go. Okay, cool.
Do we need to take
If
the
you
microphone?
want, I'm not sure if it's been working, but just for
Really?
yeah. So maybe it might start working, but if you want to hold it, at least in case, doesn't hurt to hold it. Yeah.
Okay, that's good.
Okay. Are you guys good to go?
Yeah. Yeah, don't know if someone's calling, maybe.
Okay, we'll get started. Go ahead.
Okay. Hi everyone, my name's Leonardo. I'm from Team 52, a Sapienza rocket team from Rome, Italy. I'm the project manager of this year's competition project that is called Medusa. She's Sofia, and she's the head of our structures department. We will be presenting an overview on design, analysis, and manufacturing of composite sandwich fins that are intended to be mounted inside of a modular fin canister architecture. So here you can see a photo of our fin canister. The main requirements for the design were the ability to assemble and disassemble it for easy transport, and that is because being an international team, we need to fly in with our rockets, so it must come down to the smallest pieces possible. And also the ability to substitute a single fin in case it gets damaged during the test flight. And this is a little bit of a foreshadowing for later. We'll see what happened with the test flight. One other main concern was being as lightweight as possible while maintaining an adequate safety margin on the aeroelastic flutter stability. Okay. So in order to attach each fin to the 4 aluminum rings of our fin canister, we decided to integrate an aluminum insert inside of the fin structure. It is integrated during the layup process. And there's the need for this aluminum piece is to efficiently transfer the loads from the fin to the fin canister and then to the entire rocket assembly. Okay, here you can see a section of our fins. There's the aluminum here in gray, then there's the carbon fiber, and the yellow is the core material. So we have a adhesive film that is put at the carbon to aluminum interface to improve bonding. And then we have decided to put a protruding bulb geometry on the aluminum insert. This, together with the reinforcement in the middle and the active core material, provides a mechanical interlock that assures the integrity of the entire structure. The carbon fiber reinforcement on the inside also contribute to the overall stiffness of the fin, but the main action for stiffness comes from the outer skins. The core inside is called Coridian, and it is produced by our partner company that helped us with the manufacturing of the fins.
So, in order to find the best configuration in terms of our elastic stability, we decided to perform a series of finite element analysis, both on an airfoil configuration and a flat plate configuration. And through the Nastran solvers 103 and 145, we were able to assess model characterization, so how the fin behaves in terms of model shapes, and fin flutter velocity, as well as the optimal number of plies per skin. So let's start by talking about how Nastran, which is the software we used, performs the analysis. So first of all, the model consists in a superposition of two meshes, an aerodynamic one and a structural one. And basically, the solver 145 takes the two meshes and couples them through linear interpolations of nodes. And the aerodynamic model is that Nastran used is based on the doublet lattice method, which basically takes the aerodynamic lifting surface and discretizes it in panels through the chord and the span of the fin. As for the structural model, the structural model comprises geometry, material, and boundary conditions definition. And I'll talk a little bit more about it later. So the first aeroelastic analysis we computed was done on a flat plate configuration, 4 mm thick full carbon plate configuration, which had the same plan form of the airfoil one. And the simulation was conducted on a Mach range between 0.1 and 6 at sea level air density, and considering only the first four model shapes of the fin. And as you can see from the root locus diagram, which is this graph here, so basically this graph plots the evolution of the first four model shapes with respect to velocity. Hence, each point corresponds to a different airflow velocity. And on the axis, there is the real and imaginary part of the eigenvalues of the system. And as you can see, the flutter velocity ended up being at Mach 1.5. And on the plot, it corresponds to the point where one of the first of the four model shapes crosses the imaginary axis. As for the airfoil fin, this is a little bit of a characterization of the structural mesh. So basically, the airfoil was modeled as a coreless carbon fiber shell with a 2D discretization. This was done in order to avoid any unnecessary complications in terms of modeling. Hence, the core material doesn't really significantly affect the internal structural stiffness of the fin, as well as the aeroelastic behavior. And as for material modeling, we decided to model it as a two-ply laminated composite skin, which ended up being the best configuration in terms of optimal number of plies. And the fin was eventually clamped at the root interface. This was done because this was the most realistic boundary condition. So here you can see the same graph as before, but for the airfoil configuration. So the root locus diagram actually shows that none of the four model shapes crosses the imaginary axis in the given Mach range. This means that fin flutter velocity occurs above Mach 6. And it's clear, and we can safely say that the airfoil configuration was the best and most resilient to flutter instability than the flat configuration. In the end, we eventually decided to compute a final aeroelastic stability analysis. And this was done based on data resulting from our mission analysis department simulation on a nominal flight. And as you can see, the system remained stable throughout the whole flight and with a good safety margin.
Okay, now I'm going to talk a little bit about the manufacturing. First of all, I want to add that the design was entirely carried out by ourselves with a little bit of help from our partner company that gave some tips about the manufacturing processes, since they specialized in that other than the production of the active core material. The company is called Diamentis, and the product is called Coridion. Can you get the next slide, please? In here, I'm going to show some photos of our members at work at the partner facilities, because they provided the molds and the materials and a little bit of expertise, but then most of the manufacturing was carried out by our members. On the left, you can see the right skin, being laminated on the right half of the mold, and then the same thing was carried out for the left half. They are not entirely similar, because the right half has a seam allowance on the leading edge and the tip of the fin, and this will be used later. On the right, you can see the adhesive film being applied on the surfaces where the carbon fiber plies touch the aluminum insert. Going on. On the left, you can see the right core half being aligned with the help of the aluminum insert inside of the third part of the mold. After it is aligned, the insert is removed so that we can place the internal reinforcement where the bulb of the insert is. Then the insert is inserted again, and a single ply of carbon fiber is laminated right in the middle of the fin. After that, so we are at this stage. After that, another ply of carbon fiber is inserted to do the left part of the internal reinforcement, and then the left half of the Coridion core is placed. Now we can fold the seam allowance of the right skin over the left core half, and this is done so that when we mate the left skin with the right skin, there's not a tiny contact area, but it is spread over a larger surface. So the mold is then closed with 6 M8 screws, and then it is inserted inside of the press. The press applies a force on the 2 larger surfaces of the mold, and then heats them up to about 280 Fahrenheit. At this temperature, the carbon fiber prepreg starts to cure, and the internal core is activated. Once activated, it becomes a little bit more viscous and applies an even pressure from the inside. So any voids and crevices will be filled by the core, and even if there are some imperfection or tolerancing issues with the mold and the carbon fiber plies, it takes care of that. And the main thing is that it is able to push the inside reinforcement beneath the undercut of the protruding bulb, thus creating the mechanical interlock that we wanted. After 50 minutes, the curing process is completed, and we can open the press and take the mold to a shower so that the temperature can be lowered very fast. The turnaround time of this process is just over 1 hour. And with this, we were able to manufacture 6 fins in just a day and a half of work.
So here are some numbers just to sum up. So in the end, the airfoil configuration ended up having a fin flutter velocity over Mach 6, while the flat plate configuration may experience a flutter instability above Mach 1.5. And the overall mass of the single fin, aluminum insert included, ended up being 158 grams compared to the 201 grams of the flat plate configuration. And as I previously mentioned, the optimal number of plies ended up being 2. And so here we wanted to show you some of the photos of our test flight. We did our test flight about a month ago, and as you can see, it really didn't go nominal. And in fact, we unfortunately had some problems with the re-entry subsystem, so our rocket ended up planting itself to the ground at about 108 feet per second. And in the end, we had to change all 4 fins. One of the main advantages of our design, of our fin canister design and fin design, is the possibility of replacing each fin individually. Unfortunately, we weren't that lucky. And nonetheless, we were very satisfied with the result. In fact, if it was only for the structural adhesive, the composite fin would have completely detached from the aluminum insert, as it actually did where the bulb geometry wasn't present.
So if you want, we can pass around some samples.
Yeah, we got a section fin, so where you can see the internal structure. And the core material, unfortunately, they didn't cut it where the bulb is, so you can't really see it. But yeah, you can feel how light they are. So I don't know if you want to.
There's also the damaged fin. You can see that the carbon fiber detached from the aluminum insert on the back side, where the bulb is not present. But if you stress the 2 parts, you cannot separate them.
Because they are mechanically interlocked. And so, yeah, you want to thank you for your attention, and we are happy to answer any questions you may have.
I do have a question.
Okay.
Yeah. So, how was the Caridian core material chosen? Did you validate against other materials?
No. The thing is, we had a modular fin canister design from last year that we wanted to replicate in order to not revolutionize the entire rocket architecture. And we were looking for companies that would sponsor the materials to make a sandwich fin. We reached out to Aliamentis, and they didn't only provide the material, but also their expertise on the processes, and they invited us to their facilities to build the fins. So we had to change our intentions, and we started designing the fin. And after like a month of work, we got some feedback from them, and then the manufacturing process started.
Yeah, so we basically didn't have nothing about. So we weren't actually thinking about composite sandwich materials at first. So we were only trying to find a different solution from last year's, where last year's we used a flat plate configuration 3 millimeters thick, which had like a platform which was a little bit smaller than this year's, because we ended up building a bigger rocket in terms of diameter and also in terms of wings, wings platform. And we did want to keep, as Leonardo said, the fin canister design. but we didn't want to make it too much heavy. So we started searching for solutions, and we ended up finding Coridian and Aliamentis, of course. And yeah, we thought, yeah, cool, let's try that. And also we were able to make our aerodynamic department happy, because it was the first time we were able to implement an airfoil on our actual fin design. So it was, yeah, pretty exciting. Any other questions? Yeah?
Have you guys considered different configuration of fins, like 3 fins, 5 fins? What's it on?
Okay, so we chose 4 fins for a couple of reasons. The first one is that the same configuration as last year's rocket, but there's a very big reason behind it, and that is because of the symmetry planes. 4 fins, we have less of an effect of the roll position of the rocket with respect to the wind gusts than 3 fins. So I guess in our technical report we put a graph that shows how the static stability margin changes with respect to the direction from which the wind comes. And with 3 fins, we have a pattern that is repeated 3 times, and the difference between the maximum and the minimum of the static stability margin is way higher than with 4 fins. Yeah.
For the aluminum insert, is that something that you machined yourselves or your partner did, or is that something you bought?
No, so the thing is, we don't have any facilities that allow us to CNC machine or laminate with such difficult processes ourselves. So it was entirely carried out by the partner company, obviously with our specifications for the geometry and material.
So the basic design was made entirely by us, but our partner company helped us with some suggestions on the actual design, and also with the manufacturer of the aluminum insert, which was CNC machined, and the entire process, as well as the 2 molds. Yeah, the 2 mold halves were actually designed by them with our geometry specification on the fin.
Yeah, and the thing is, producing the molds is the where the cost is. Once you have the molds, if you manufacture 4 fins, 8 or 12, it doesn't really add up to the costs. So what we are trying to do with the entire rocket, and also we'll try to do this for the fins, is to reuse most of the components on next year's project that will have an hybrid rocket engine instead of a COTS motor. And the molds are there, so if we need other 4 fins, it's not going to be a real issue to get.
Did you bring any extra fins with you in case of problems?
So the thing is, we originally asked them to produce 8 fins to have a full replacement set, but one of the inserts had a manufacturing issue, and so we decided to do a test run with this, and it ended up being in the fin that was cut in half. For this reason, at the time of the test flight, we had the 4 flight-ready fins and 3 replacements. And then, after the unfortunate event, we readily contacted our partner, and they had already started the manufacturing on the 8th fin. So, I mean, it's what we predicted, what we wanted from the start, and then we were lucky to have them be a reliable partner and enable us to come here and launch, even with this close time between the test flight and the competition. And also, the damage on the 4 fins is about what you see on the fin that we are passing, and they could be. I mean, they are not entirely broken. We could lay some more carbon fiber plies on them and make them usable, but obviously we didn't want to do it for the competition.
Any other questions?
Yep.
Did you do any testing of your fins, like physical testing?
No, so after each fin was manufactured, we did a check with a 3D scanner to verify that it was in the tolerances for all the dimensions.
Unrestricted tests.
Yeah, and then each fin was thoroughly looked at to spot visual imperfections, and then we had the test flight. Yep.
Was the NDT just like on the outside of the film?
I'm sorry?
The non-destructive testing, was it just on the outside of the film? Was it inside?
Yeah, just the outside.
But actually, the 3D scanner also was able to see if there were any unhomogeneous places inside. So it was most about the quality of the manufactured fin, rather than young modulus strength and so on. But yeah, you were able to see inside through, but only to visually check for any holes in it or voids.
And also the active core is a more reliable process than other types of cores, for the reasons I was telling you about earlier.
Any questions?
Okay. Thank you so much.
Thank you for the opportunity.
Vai, riprende l'ala. Go.
Thank you. Qual è il materiale che avete usato dentro?
Com'è?
Come si chiama il materiale?
Coridion con la K. Sì, è un materiale che hanno sviluppato loro. Quindi è un materiale viscoelastico che non so se l'hai detto prima, vabbè, ad alte temperature lui è operato a 140 gradi, che sono 280 Fahrenheit, e è arrivato a 12 bar di pressione. Quindi raggiunge fino a
in base
12
alla
bar.
frazione di volume che occupa può applicare fino a 12 bar dall'interno.
Esatto, per cui ti riduce tipo tantissimo il tempo di cura. Ok, ci hanno detto tipo in autoclave questi almeno 6 ore avrebbero dovuto stare, 50 minuti in pressa induzione, 140 gradi, quindi 280 Fahrenheit e via. Quindi velocizza tantissimo il processo, considera in una giornata ne abbiamo fatte 5. E con lo stesso stampo. Quindi sì. Poi una volta che lo demoldi, una pulizia al volo è assurdo.
È incredibile, sì.
Test di trasmissione e
fantastico. No, veramente, complimenti.
Grazie.
So we'll see you later.
Yeah, 2:30 you said, right? Yes. Okay.
We'll be at our stand.
Awesome. Thank you.
Thank you.
now for our purposes. Not Athena. That's the rocket group here. No, we already did the prophecy, bro. We can't reuse Rocketry. Mark 2. We're not reusing the prophecy was last year, wasn't it? I'm all for Rocketry. It was. We're not reusing Rocketry.
You know that one white and black rocket in the closet?
The Prophet?
Yeah, that's called Prophet 2, I think so. So there was a Prophet 1 as well.
That's lame.
What?
But pollo is chicken in Spanish.
It's also, we looked it up, it's also probably not, it might not be how you pronounce it in Norwegian, but I think it's funny. So let's choose it as Norwegian. I don't know. Not good.
Not who's who's. No, they're pulling up. We still got 4 minutes, right? Why don't we do it? That's the better question. This is a crazy microphone. Where's the rest of the squad?
Where's the rest of the team? Where is everyone?
Some people gotta stay back.
Who's Dean's done back? Who's recording? Who wants to record?
Where's MFR Reese?
Well, yeah, but somebody should record. Because I don't know what that camera is. There's no camera in the camera.
I don't know what Max has been
There
doing.
is?
I'm gonna be honest. I've like seen him twice.
Oh.
Something with food and that's it.
Yeah, but I want a video for now.
Are there going to be?
You can have one for later.
I don't know.
Yes, no, it's just us. How long did you guys present?
30 minutes.
Oh.
We get 20 minutes for the presentation and then I think 10 minutes for questions. Although there's a timer that indicates 25 in the back, so I don't know what's going on. Joe, where's your shirt? Joe, where's your shirt?
Wait, can I sit front row?
Where's your shirt?
I brought it for pictures.
Oh.
I'm sorry.
He was not one of the washing machine members.
No, we gotta like find a laundromat or something because Marcello needs to do his laundry.
My laundry is drying.
With the title slide in the background, I guess.
I can like.
If I plug this in, am I gonna break something? James Lee, if I plug this in, am I gonna like break something? Oh, good thing. He went somewhere. Yo.
I'm a photographer, not a paparazzi.
Is it true?
Just be yourself.
You're presenting too, bro.
Oh, right. Oh, frick. Oh, no.
Alright, this works.
Dude, just get the brisket torta after.
I'm getting that.
I feel like a new man.
The brisket torta.
I was like sick this morning. I'm ready to run 5K.
Okay. Well,
Just
when
like
are we
you.
running 5K?
No, I don't want to run alongside. We should
IREC 5K.
We should do sprints tomorrow in the 108 heat. Yeah, and see who passes out.
No, that's not a good idea. In no world is that a good idea.
Free dinner.
They win the
What?
competition.
What? Desert 5K? Instead of driving out to get the rocket, we all bomb.
But whoever wins.
Whoever gets to the rocket first gets to keep it.
No, I just, yeah.
I was like,
Our advisor right there.
James Lee.
Hello.
James Lee, you're also presenting.
Oh, right. Oh, shoot, I forgot.
Do you want me to read the title one shot?
I can do the title.
No, I'll do the title.
Okay, sure.
Okay.
If you want to do the title, I'll stop you.
Might as well. Yeah, but I don't know what we're doing with it.
Holding it, probably.
All right. Hello. What is the method for this? Do we have to use the microphone? What's...
Oh, I have no idea.
Okay.
It's on.
It is on, but where does it go? That's the question. Doesn't really do anything. I'll just talk loud, it's fine. Is the camera recording? That's the question.
Just hold it.
Hold the microphone? Yeah. I'm not gonna hold the microphone.
Okay.
All right, let us know when you're ready when we begin.
You did.
Okay.
The other judge had to take a phone call, so he's a little bit late.
Okay. As long as we're good to go, we can. Okay. So, hello everyone. My name is Brody Schneider. I'm the recovery sub-team lead. We're doing the microphone? All right. Okay. So, hello everyone. My name is Brody Schneider. I'm the recovery sub-team lead for the Rowan Rocketry team. We're team 83 here at IREC, and we're giving a podium session today on the design and additive manufacturing of our Inconel Chargewells for improved recovery system reliability. You want to introduce yourself as well?
Hello everybody, my name is James Lee, and I'm the team captain this year for Rowan Rocketry. So here we're going to offer a brief background of the Rowan University Rocketry team. One way that we're a little unique is that while a lot of teams here at IREC are student clubs or extracurricular organizations, we're actually a class that a lot of people sign up for. So we have a junior-senior engineering clinic program that runs very similar to a senior capstone project in many schools. We sign up for something that we participate in for 4 semesters. It could be a research project, it could be a competition project, something where you build something. One such clinic class that you could sign up for is a class where you design, build, test, and launch a rocket every year for the International Rocket Engineering Competition. So here in this picture is our team for this year. It is 26 different junior and senior mechanical and electrical and computer engineering students. So the main overview of this presentation that we're giving today is on the design process of our Chargewells over the last 3 years. We're going to talk about the design history from 2024 to 2025 to this year. We're going to talk about some things that we changed this year and some obstacles that we faced. And then we're going to talk about the advanced additive manufacturing techniques that we employed for the first time this year and some of the lessons that we learned through doing so. So first, I wanted to start with a design history of the Chargewells from the last 3 years. So we started consistently attending the IREC competition starting in 2024. In all 3 years that we've been here, we've been in the 10K COTS category, and we have utilized black powder as our primary separation mechanism. In all 3 years, we have used a novel recessed Chargewell design. So instead of attaching the Chargewell to the outside of the bulkhead and having it stick out into the parachute bay, we actually do it a little differently where we screw it into a threaded hole from the inside of the avionics bay. Traditionally, we've had very long avionics bays with a lot of space in the inside. So we did that as a way of saving space in the recovery bays. And that's also just been the way that we've done it in previous years. We do that through threading it from the inside. The first one that I wanted to show off here is the design from 2024. This was the first Chargewell that we made ourselves. It was made with a piece of 1/2-inch aluminum round stock bar. What we did was we bored a hole through it through the entire inside. We have male threads on the top, which is what we use to screw it into the bulkhead itself. And then we have female threads on the bottom that's interfaced with a 3/8-inch bolt. That bolt has a hole drilled through the middle of it, and that hole is what routes the E-match. Now this design worked. All 4 black powder charges went off successfully. The rocket successfully separated, and the recovery equipment successfully deployed. There were some negatives with this design, though. The primary negative was that once you screw it in, because you twist the bolt into the Chargewell by twisting right, and then you twist right to get it into the bulkhead itself. Once you take a wrench and twist it left to unscrew it, the bolt comes out, but there's not really an easy way to get the Chargewell itself out because there's nothing to grip onto. It may be a little difficult to see there, but we had to take a vice grip and clamp it really hard and then twist the bulkhead like a steering wheel to get it out. Now, while that's possible, it's definitely not an easy way to do it, and it's marred up a little bit. So there's an easier way to get the Chargewells in and out. In 2025, we wanted to iterate upon the previous years by taking a milling machine and machining our own flats onto the underside of the Chargewell, and then we just drilled a hole through the underside to route the E-match. We're able to get the Chargewell in and out of the bulkheads much more easily now, and this is what we successfully used last year. But during our flight safety review, we received some comments about this design. I remember being told that because our E-match head is at the bottom of the Chargewell and it's sticking up from and it's going to ignite from bottom to top, a lot of the black powder is actually getting spit out as it's initially combusting. Not all of the black powder is burning. So while this may not be a problem at lower altitudes, in future years, if we're going for higher altitudes, because we're not optimizing the pressure difference, this may become a problem for actually successfully separating the rockets. So the next slide, we can talk about the design changes that we wanted to propose for this year. So it's the same core design as what we had in 2025 with one key difference. As you can see in that section view there is a channel that we implemented along the inside wall of the Chargewell. Because the E-match is a solid core wire, we can just pinch it and have it aim downwards. So we stick it through that hole, and then we pinch it, and then as it's aiming downwards, it'll burn from top to bottom instead of bottom to top, which in theory helps burn more of the black powder, creating a more efficient combustion. Now, while that's a pro to this design, there is one negative, namely we used a lathe to machine the previous two designs for the Chargewells, and with this intricately designed E-match routing channel, you can't easily get a drill bit in there to bore out the hole without also eliminating that channel there. So we needed to find some other way to manufacture this. Now, during my 4 years at Rowan University, there was a new organization that was created, and I had the chance to talk to them during the fall semester of my senior year. They're known as the Rowan Digital Engineering Hub. It's an organization of graduate and undergraduate student employees that helps harness advanced digital engineering methods to solve problems. Some things that they do include additive manufacturing, digital twins, and data-driven design. Some things that they accomplish are metal 3D printing, materials testing, and non-destructive evaluation. When I had the chance to talk to them and learn about what they can do, I figured it would be a pretty cool opportunity to work together with them, not only to do something interesting, but also to learn some cool lessons about what they know and how we can introduce that into our own workflow. So the specific thing that I wanted to do with them was their brand new LaserTech 30 SLM 3D printer. So this is something that Rowan University actually installed during this school year. It's a selective laser melting 3D printer that uses metal powder to produce complex, high-strength parts directly from just powder that you could buy in bulk.
So I'll take over. So in order to determine if going with the metal 3D printed Chargewells was adequate for our use case, we used finite element analysis in SolidWorks. We simulated a 1000 psi internal load on all of the internal faces of the Chargewell. This resulted in a factor of safety around 33. The 1000 psi is dramatically overstating what will actually be experienced during flight, as most typical black powder ejection charges are around 15 psi. So we have plenty of safety margin if we were to go down this route. Our conclusion was that the Inconel Chargewells would be extremely robust for this application, so we did end up pursuing a collaboration with the Digital Engineering Hub. The manufacturing process, we ended up choosing to use the additive manufacturing using the SLM 3D printer. We selected Inconel 718 as the material. We selected this because since it is a new technology that the school has, this was the only material that they had available. They're working on getting more, but the Inconel was what they had available for now. And as the FEA simulation showed, it has plenty of safety margin. It's honestly kind of overkill for this application, but it's better to be safe than sorry. So more than adequate. After we produced them on the metal 3D printer, we ended up having to post-process the machine threads because they weren't 100% sure of the capabilities of the printer yet. They preferred that we didn't try to print the threads. They weren't sure how they were going to come out, and it's fairly expensive to use the machine, so that's why we ended up post-processing them. However, Inconel is too hard to post-process without specialized tools that the university didn't have. Annealed Inconel has a Rockwell C hardness of between 30 and 35, and most of the tools that we had available wouldn't have been able to machine it. So we annealed all the Chargewells using a heat treating procedure to decrease the hardness. After annealing, the hardness dropped to around 20 to 25. So we were able to machine them. Before we did that, we 3D scanned on both ends of the annealing process. So we took a 3D scan of the Chargewells before the annealing process and the after the annealing process in order to see if there was any dimensional change in the Inconel part. We found that there was no significant dimensional change, which was similar to what we had read would happen. This indicates that the overall stability of the Inconel is very high, and the dimensions don't significantly change during any sort of heat treating process. Finally, we added the bulkhead interface threads with post-process machining. We used a lathe and then a die to cut the threads, and then the bottom picture is the Chargewells installed in our avionics bay. I meant to bring one of the avionics bays to show off the Chargewells. Unfortunately, I forgot it. It's back at our table, so the picture will have to suffice. We did successfully implement them on this year's vehicle. This is a couple of screen grabs of one of our ground testing videos. We deployed on the launch vehicle and used them for extensive separation testing. They have held up well so far, and we confirmed the theory that the top-down black powder burning would significantly limit the amount of black powder being expelled. We can't find any traces of black powder being expelled, so we believe that all of the black powder is being burned during the ejection charges. Another side note is that these Chargewells were the DE Hub's first successful student project, and this demonstrates the capability to use their technology for student collaborations in the future. A couple of lessons learned from this is the Inconel parts changed color during the annealing process. We believe that this was the result of oxidation between the primarily chromium and nickel components of the Inconel and the trace oxygen in the vacuum bag. The color change is purely aesthetic. It doesn't affect the overall mechanical stability of the part, and because our theme for the year is Night Owl, we black and gold, it fits with the theme better, so that's what we like to tell people. Additionally, we learned that the software for the LaserTech printer has different settings for approximation of various shapes, in our case a circle. We ended up accidentally selecting an inscribed circle instead of a circumscribed circle, so the part was overall smaller than we expected. However, it was still within tolerance, so we could machine the threads. It didn't end up affecting anything, but it was a good thing to know and to learn from the software for any future projects. Yes.
One final lesson learned, as well as just like a general statement. I understand the purpose of competitions like this are to foster learning environments to do new or novel things that you may otherwise never need to or get the opportunity to do. So the direction that I wanted to take the team in this year was to put us in the position to do things such as this that we otherwise wouldn't get the chance to do. And the fact that we were the first student project to print on a brand new printer as new and experimental and as expensive as this is something that I'm really proud of having the chance to do. There was a lot of hoops to jump through. There was a lot of research to do, a lot of design reviews, a lot of reports to write. But after doing everything the right way and getting it done, at the end of the day, we learned a lot of cool lessons, and we also came out of it with a very cool story to tell. So I'm very happy with what we were able to accomplish with the Chargewells this year. And lastly, some acknowledgments that I'd like to give. So the Rowan University Digital Engineering Hub as a whole, with all the help that they've given. The organization is led by Dr. Antonios Konstos, so big thanks to him. Dr. Charlotta DeVries, who's actually in the back right now, she's our advisor for our team, and she provided a lot of guidance for everything, but especially including everything that we needed to do for the Chargewells this year. And Matt Leoncini, he's our department technologist and the person who runs the mechanical engineering projects lab. He was a person who helped us a ton with the post-processing of like the annealing and the threading and all that. So he was also a very huge help in getting these Chargewells done. So thank you a lot to everybody in this list.
We don't have a question slide, but that's the end of our presentation, so we'll open up the floor for questions. Thank you, guys.
So your objective is, clean combustion of black powder. I think putting the EMAX on top is the smart idea. I'm curious if you did any optimization in terms of length of the Chargewell, in terms of like allowing it to combust.
Yes, so I'll take the mic. We did do a little bit of optimization, so we know the density of black powder. We knew how much black powder we needed at this point, so I designed the Chargewell specifically to hold a specific amount of black powder. It maxes out right above 4 grams. I think the max I can fit in is a little over 4.1. Our backup charges are 4 grams, and then our main are 3 grams, so it is optimized for length. If it were need to be changed in the future, say we went to a bigger airframe, bigger rocket, we need to do something like that, you would simply just lengthen the length of the Chargewell. It's a super easy change to make, and then they would just be reprinted.
So there's no volume above the black powder in them?
There is a little bit, because the channel doesn't go all the way up the side, because the E-match needs room to route around the top. There is some volume above that. However, we would prefer not to fill the black powder up to there, because some could theoretically fall through the channel into the avionics bay. Yes, we seal both ends once we install the E-match with hot glue. We tested that during our ground testing. It worked perfectly fine, so that's what we're doing at the competition as well.
Additionally, our backup black powder charges are 4 grams, so that's what I understand to be a decent amount of black powder. So I think it's pretty like future-proofed for.
Curious, like there's a lot of, especially for high altitude stuff, you're interested in clean combustion, especially getting all of it right. If you have a longer tube with more volume in it that isn't black powder, you can also get more clean combustion. So that might be something you could look at longer term in terms of like taking this and then adding almost like a barrel. You can get even cleaner combustion.
God, that's a good idea. Thank you.
That could be definitely something we look into next year. So thank you. Other questions?
Yes, I have one question. You validated your model using a simulink with a flare camera. How close was the result with the actual temperature?
I don't think we did. We didn't do any temperature studies on this.
We did not do any temperature studies, but we were told to refer to the product data sheet for the Inconel material and to check out like the melting temperature and all that. And we knew that like temperature-wise, not only hardness-wise, but also temperature-wise, the Inconel was way over-spec'd for this application. We didn't need to worry about any thermal stresses or strains that would be applied to the part. Yeah, that's a good point. It is a very strong material for this application, but like we said, because that's the material they had available, that's primarily the reason why we used it. But I mean, it is a good thing that we know it shouldn't break anytime soon. Any other questions? Yeah. To be able to say we have Inconel in our rocket is pretty cool. Anybody else?
So if there's no other questions, thank you everyone for attending. That will conclude this podium session.
You guys. Thank you, James. Thank you, President.
Uh-oh. Can I have that?
That's really good.
Yeah, thank you.
That went very smoothly.
Yeah.
What color's the rock?
Where'd you get the cowboy hat?
Thank you.
It's just kind of baller to have him.
Yeah. That was, they told us, like, that's the material we have, and we're like, it's so overkill, but sure, why not? Like,
Why not? Exactly.
like the aluminum was perfectly fine last year, and Inconel has the multiple double-digit increase over that.
Yeah, I know some people use PVC pads for Chargewell.
Yeah. Some people use PETG 3D printed for Chargewells.
I'm a brass guy. So
I've seen those before, yeah.
So
I like the putting on the top. It's not something I like. We sync like in my old team, and when I fly personal rockets, we sync our black powder. Like we sync them all at the bottom. And I didn't think about that for clean combustion, but definitely look into adding more length to
More chamber, yeah.
Because the resonance time in the chamber will also provide clean combustion.
Okay.
So we don't have any issues with exploding black powder either, even though we're E-match on top. Though I'm probably going to try to start putting them on the bottom to get even more gas generation. But what we do is we'll put the brass, so we'll put the black powder at the bottom, and we'll actually pack the excess volume with Estes wadding because it's just fire retardant tissue paper, and then instead of hot glue, and you could probably do this with these as well, especially when it's total. You can put 5-minute epoxy as a layer, so that it actually pressurizes it more, so you get cleaner combustion because it takes longer for it to burst than the hot glue does.
We looked into epoxy. We need the E-matches to be able to be pulled out, and epoxy isn't super great with that, especially if it's quick setting epoxy.
Well, you just put it on the. Well, yeah, you might run the risk of pushing your gas to the other side.
Yeah.
Yeah.
We had looked into that. The hot glue was perfectly acceptable for it. We tested it. We did a couple of ground tests with the hot glue in it. It barely moved, even with the hot temperature from the black powder. So it's more than acceptable. So
It's pretty cool though. I like it.
Thank you.
Yeah. I think
something that was a lot of my spring semester was fighting with the D to get that done.
Yeah. It's a fun project. Like very, at least for me, it's like I don't. It's poor black powder. Good. So it's cool to see something with like a lot of detail and really thought into.
What we excel in is going into extreme detail on specific things.
Yeah, just like random things, we'll just like obsess over everything.
Yeah, Chargewell is a perfect example of that.
I mean, looking at rocket stuff, you have a lot of areas that I can tell like you just put a lot of time in and look really good and they're very functional. So I mean, it's not a bad way to do rocketry at all. So.
Yeah, I really like what you said when you were at our table. How like instead of like focusing on like a ton of stuff and doing a ton of stuff like average or poorly, we just honed in on like certain things we knew that we wanted.
Yeah.
And I'm glad you said that because like that's the exact thing that I said to myself in like the first day.
Yeah.
Like that's like what I wanted to do.
Oh yeah.
And I'm glad we were able to like accomplish doing that.
It's very apparent. It's very clear that it's the things that you went after very intentionally thought out, and it was like, how can I make an improvement without like just maximum scope creep, and then we're running around with chicken egg head so trying to like keep up. So good work, guys.
Yeah, thank you
very much.
And best of luck on your flights.
Yeah,
thank you.
We're sitting in the hallway there. There's a team right there.
But they have sparks in it. What? Like, they don't really close to
No, it's traveling right into their face.
I was like sitting there and I just saw a bunch of sparks came out at me.
That's valid.
Not me.
To be clear, it was not us.
I was sitting.
I have a red form in here I can give you.
It's not 2 feet.
I would give them a red form if I saw that though.
Sitting next to
I mean that's valid.
Just valid, but I also.
You know what? We should have said something.
I wasn't thinking that.
If I choose something,
I actually didn't even notice. Where do you start?
black powder? No. I was saying if there's something like that.
Or
Yeah.
Yeah, exactly. And I'm pretty sure it's so far still in half the rocket products. So even if it was like a lot of scared parties, we were able to do it at the end of the day. And it's something that they can
I can coincide stuff. That's
that they can
show
show
never in a million years.
potential like
What'd you do undergrad?
outside people like
I actually like see the
I competed in 24.
So I feel as that all parts that
We do like every track right? So I'm in the list. We could be in our Gurney Cup, so we like finish our Gurney Cup in March, and then we start the rocket. So we have like the last week of March, all of April, and then May till St. Week. So yeah, we don't do a lot of testing. We just build rocket.
Wait, so why don't you do it every other year?
Because it's expensive. We like their Gurney Cup more, so we do that, and then our advisor wants us to come here, so we
Yeah,
It's a great process. You guys should come out and experience it. It's hard. We won a few times, and then we like lost our knowledge base, and took a lot of time for us to get back. We got the second too, which I was respect about, but oh man, it's a juicy contest when it comes to design.
Because it's just like golf balls
and two stage. It has to be two stage. But it's a great contest, and it's fun. So. But it does make IREC interesting.
I can't imagine that's what
every year they would say, because I was always more check for I was a director for a while, but I always so they'd be like, oh, this is the year we started in the fall. We'll start rocking the fall, and
then you get busy.
Then we built our Argonia Cup rocking the fall. That's why I didn't fall, but it breaks in half for it. Yeah. Fun. I think y'all are good to start. We're a little early, but I'm not opposed to getting done early. So.
All right. Yeah. All right. Well, thank you all for coming out. We are Northwestern NU Stars. I'm Mason.
I'm Pavi. And I'm Amelia.
And we're super excited to share with you today our split ring modular fin can and motor retention system.
So to tell you a little bit about why we decided to undertake this project, in past years we've flown with the NASA student launch competition, and we actually decided to make fin clamps. So these were 3D printed ABS fin clamps that were directly bolted onto fiberglass fins. And while the system was successful in flight, these flights were only up to about a 5,000-foot apogee or lower. So this was not quite what we needed for reaching 10,000 feet at the IREC competition this year. And so for our first ever IREC, we decided to take the system, improve it, make it more robust to reach our targets for aerodynamic loads this year.
Also, should we speak to the microphone? Or
does everyone hear him okay? Yeah.
Okay.
Okay, perfect.
That's personal preference for them.
So that leads us right into our design requirements. As Pavi just mentioned, this rocket, unlike last year's, has to fly in the transonic regime. So that means increased structural and aerodynamic loads that we have to handle. We also wanted to meet IREC's 50% fin flutter margin requirement. We aim for individual fin replaceability without having a full system assembly. And lastly, we wanted motor retention without a traditional motor mount tube. That led to the additional design requirement that any material touching against that motor casing had to withstand a temperature about 230 degrees Celsius.
So getting a little bit into the general system overview, as you can see, our fin clamp design has roughly four main parts. We have our fins, which are tapered swept design and have 3 bolt holes through the root cord. We have our top centering ring, which is in the green, or we also call it the forward centering ring. We have our middle split ring centering ring, which is the yellow. We call these our bananas. I'll talk about it a little bit more later. And then we have our bottom centering ring, which is our thrust plate. This is where the motor is retained with a motor retainer that bolts directly to our thrust plate, and this transmits the force loads into the rest of the rocket. So for the centering rings as a whole, they are all made out of 6061 aluminum, along with the fins. And this satisfies that requirement of the motor casing of withstanding that temperature of 230 degrees Celsius. So then talking a little bit more about the centering ring specifically, you'll see that they all they all connect to the fins with steel fasteners in the root cords. All these steel fasteners are connected with nylon nuts to ensure that vibrations don't cause the fins to come loose. And then this whole system is here to boost your airframe with radial connections that bolt directly through the airframe into our centering rings. So getting into the specifics of each component, we have our fins, which are tapered swept design. As I mentioned, they have 3 bolt holes through the root cord. For the top and bottom bolt holes, those are a specific distance away from the edge of the fin. We calculated this distance using an edge diameter ratio to make sure that stress concentrations were low and not high enough for in-flight loads. Then for the middle bolt hole, we calculated the center of pressure of the fin, and then we placed that bolt hole in the same plane as that center of pressure so that the middle bananas would effectively constrain and reduce moments from that flight loading. So then talking more about the centering rings specifically, all of them have about 4 brackets. The bananas are a little bit weird. I'll talk specifically about them. For our thrust plate, we have those 4 brackets with a flush side and a filleted side. That flush side is where the fin sits against, and that is where we bolt everything to. And then we have some through holes through the bottom of the thrust plate. We added these so that the system would be more mass optimized. And then we have our radial connections to the thrust plate, which are a little bit visible at that 45-degree angle between those fin brackets. A little bit more about the thrust plate. The motor retainer bolts directly to the bottom, and then along that mating face between that motor retainer and the thrust plate, that is where the thrust load is transmitted. And then the motor is retained by our motor retainer with the part that threads in to hold the motor in place. And then the motor is centered by all of the centering rings. And this eliminates the need for a motor mount tube. So we don't have a motor mount tube. We have the motor casing just directly in our system. So then the last thing about the thrust plates is that on that outer diameter, there is a little bit of a lip. It sits flush with the outer diameter of the booster tube. This is the main area of transmission for the thrust force. It acts from the motor to the motor retainer to the thrust plate, and then from that lip into the booster airframe, propelling the rocket forward. Moving to our bananas, these are 4 separate parts. They are not connected together by any aluminum. They are connected together in between the fins with our seal bolts and nylon nuts. The way that we gave them the name is because they are all a quarter of a circle or a crescent, or as we like to say, a banana. We colored them yellow to make this even more fun. So then for the last centering ring, we have our forward centering ring. This is extremely similar to the thrust plates with its brackets and radial connections. The big difference is that there are no holes through the bottom of it. This is because just above this centering ring, we have our drogue parachute and payload, which we want our ejection charges to be able to create a positive enough pressure to effectively separate the vehicle, release drogue, and release our payload.
All right, so one of the main principles that guided our fin design this year was fin flutter. We wanted to ensure we had that 50% margin between our max flight speed and our flutter speed. So this year we did a different method than we had done other years. That's because the NACA formula that we used before had a denominator constant that really only applies to symmetric fins. We're looking at a lot of designs that were asymmetric, so we looked into John K. Bennett's method, which corrects for this constant, but it also makes the formula more conservative. We also made conservative assumptions for the temperature. As we all know, Midland is very hot, and at those temperatures, fins can flutter at a lower velocity. With all of this in mind, when we started looking at materials, we began with G10 fiberglass, just because it's the material our team had used every other year. But when we began looking at designs, we couldn't find any design that met that 50% margin requirement, but then also that didn't have a very heavy blow on apogee or stability. So we switched to aluminum 6061 because it has a 5 times higher shear modulus. And that gave us freedom to completely optimize our design without having to worry about fin flutter. So final results for flutter velocity and divergence velocity are displayed on screen, giving us a final fin flutter margin of 87.85%. As a quick comparison, if we look at our final fin design and we calculate for flutter speed but using G10 fiberglass, it gives us a flutter speed of 762 feet per second, and that's below our maximum flight speed. All of this was supplemented with Aerofin UG unsteady analysis, and it gave us an even higher margin, so we can worry about it.
So now moving a little bit to the structural analysis, we are using an M1315 motor, and this from OpenRocket gave us a thrust force of about 1,728 newtons. And with using the values from OpenRocket along with the values in the table here, we calculated the fin lift force. We used the 2 equations that you see just beneath the fin lift force to get the coefficient of lift, and all we need is an estimated angle of attack to get the coefficient of lift, and then the fin lift force, which is the standard fin lift force equation. So for the angle of attack, we estimated about a 6-degree angle of attack, which gave us that coefficient of lift of 0.657. From there, we used the density of air. We used our maximum velocity, which we got from OpenRocket, and then the fin area, which we got from our CAD. This gave us that fin lift force of about 568 newtons. You can see in the picture as well in the diagram, we have the thrust and fin lift force. We have the arrows pointing to generally where they will be applied. You have that thrust force and that motor retainer on that thrust plate. And then you have the fin lift force around the general area of the center of pressure, at least shown in this diagram. And then this whole system slides in and out of our aft airframe. So we have it so that those 4 radial connections are screwed in once we slide it in. And then after we secure our whole fin system, we then slide in our motor and then secure the motor with the motor retainer.
So we began doing FEA on the thrust plate and the top centering ring, and we had factors of safety of above 15. So we decided to remove material from both components. For the thrust plate, we used lightning holes and we removed about 0.28 pounds. For the top centering ring, we used pockets and we removed about 0.14 pounds, and then we ran FEA again. So looking at the thrust plate, we modeled that thrust force, the normal and drag forces on the fin brackets. We used a 1 millimeter mesh and then applied a fixed support at the bolt posts that represent that connection between the plate and the airframe. And the results were a maximum von Mises stress of 53.9 megapascals, giving us a safety factor of 5.1. And that stress was located at a lightning hole. And then moving on to the top centering ring, we used a very similar procedure for analysis where we had a 1 millimeter mesh, those drag and normal forces at the fin brackets, and then that same fixed support at the bolt posts. And we had a maximum stress of 64 megapascals at a pocket edge, giving us a safety factor of 4.3. To put all of this in context, the yield stress of aluminum 6061 is 276 megapascals, which means both of these components are very far away from each other.
So now looking at the whole system with the booster airframe included, we modeled this all first applying our boundary conditions and our forces. So we put our thrust along that mating face between the motor retainer and thrust plate, and then we put our fin lift force on 2 fins in the same plane. This mimics the case of the rocket coming up the launch rail and having a high tilt or high angle of attack, causing a worst case scenario of a high corrective fin lift force. So with these, we also applied the fixed support at the forwardmost area of the booster airframe. This simulates the thrust pushing the rocket forward, or it simulates it's pushing the rocket forward. And then from this, we meshed all the components. We used a 3 millimeter mesh for our centering rings and for our fins. And then for our booster airframe, we used a 10 millimeter mesh and refined that around the bolt holes. For our bolted connections, we modeled them as circular beam elements with frictionless contact surfaces. We did this along with the mesh sizes to give us this correct numbers with the most efficient computing time, because we're limited by the systems that we have to compute these analyses, so we wanted to get good values with effective use of our systems. So from all this, we got a maximum von Mises stress of 140 megapascals, and this occurred at the thrust plate and airframe connection point, radial connection hole. This is the area that we expected this stress to occur because of that geometry of the booster airframe, how thin that area is between that bolt hole and the bottom of the aft airframe. We did use edge diameter ratio as well for sizing this distance between the bolt hole and the aft of the booster airframe, and this still let us know that this would be the area where we expected this max stress, but it is beneath the stress of our material. As you can see with our safety factor, it gave us that 1.79 safety factor, which is above our minimum of 1.5. And then for the bolted connections, we had a minimum bolt safety factor of 2.37, which is also above our minimum of 1.5. So now moving a little bit into manufacturing. We used a CNC mill to make all of our centering rings. And we use Fusion Cam to model the tool paths and then optimize the tool paths to give us tight tolerances along with a quick machine time, including those tight tolerances, like still having those tight tolerances.
And then we took these rings all the way over to the conversational mill and the rotary milling index that you see, and this allowed us to drill and tap those precise radial holes to allow this entire system to be put into our booster airframe. After this step was done, we were able to separate those bananas so they would be individual brackets themselves.
So then moving to the fin manufacturing, we used flat aluminum stock and used the water jet to get precise dimensions of our fins and precise dimensions of where those bolt holes are located.
And the final step in manufacturing our fins was to create that nice leading edge with an angle. So we used CNC chamfering to do this to create an angle of about 41 degrees. Moving on to talk about some of our testing. Once we had manufactured and assembled this system that you see on the table, we decided to conduct a fin deflection test. Now, the purpose of this test was to validate our physical system as well as compare it with some of the FEA analysis. So the setup for this specific test was the fin can itself was clamped vertically using a 90-degree angle block, as you can see in the image. And the load was applied at the tip of the fin about 1 inch from the leading edge. And this was to ensure that we would have maximum deflection and simulate kind of a worst case bending. The loads were measured, they were metal weights, and they were measured with this crane scale, which is the orange scale over there. And the deflection itself was measured using a height gauge just on the surface of the fin. Now, the results from this test, we were able to apply up to 150 pounds of force. But the one that we were really concerned about was about 128 pounds of force, and this aligns with that fin lift force that Mason had calculated earlier. Now, we found that with FEA, the maximum deflection was about 0.24 inches. However, when the physical system was tested, it was about 0.54 inches. And this is quite a significant difference, and we believe that this is because of rotation in the fin can, because of inadequate clamping, and is something that we will keep in mind for future similar tests. However, we know that there was no plastic or permanent deformation since the post-test deflection measurement was about within 5 thou of the initial flatness of the fin. We're proud to say that we've actually flown the system in our launch vehicle 3 times, and it has been very successful all 3 times. Through visual inspection of the launch vehicle taking off, as well as our onboard video system, we've seen that this flight has been stable with no flutter or structural anomalies occurring. And although we haven't actually broken a fin on the field and had to replace it, we've been disassembling and reassembling this entire system between each flight. So we're confident that we will be able to fly again with it this week.
So looking at what our whole system is, what we have done, we've concluded that we have successfully designed, manufactured, and flown our modular fin can system for a 10,000-foot apogee vehicle. Looking back at our motivation, we believe that we have achieved success in improving our last year's design, going from an apogee of 5,000 to going to an apogee of 10,000, and effectively creating a system that will take on and sustain the increased loads and forces during the flight. Looking at our fin margin, we have successfully validated our fin geometry with that 87.85% of fin flutter. Of course, those are aluminum 6061. For our full structural analysis of our assembly using finite element analysis, we have validated that with our safety factor of 1.79, which is above our minimum of 1.5. And then for deflection testing, we have confirmed that there was no permanent deformation under flight loading. So that validates our manufacturing and fin design. And then we were able to field replace a fin in under 10 minutes, which was a team drive requirement, to make sure that the fin can was not the thing holding us up if a fin were to break and we needed to refly.
So for future work, we'd like to do a fatigue behavior study between the split ring retention system that we have and then versus traditional epoxy methods. We also want to reduce overall the amount of fasteners we have and the mass of the system, just so
the assembly is simpler. Something else that we want to do is to refine our FEA model as well as our experimental setups, as you saw with the fin deflection test. And this is just to validate our physical systems and improve the accuracy of these tests. And lastly, we would also like to see if we can improve this design to become more adaptable. This design is already quite modular. We can replace the fins with different geometries and so forth, but we would love to see if we can have this system implemented in varying diameter launch vehicles or to accommodate different size motors as well. With that, we are very excited to fly the system this week, and thank you so much for listening.
Now it's questions.
First of all, fantastic. Good presentation. Great FEA as well. Very impressed by that. Few questions for you though. Excuse me. How'd you estimate your 6-degree AOA? Like, in terms of like your worst case, why was 6 degrees your worst case?
We picked that value. I wasn't the full one that did the analysis to picking that. A member who is sadly not here was the one to pick that value, but
this was also based off of the IREC launch angle that was provided to us. So we estimated that if this was the angle at which it would be taken off, that would be kind of the worst case of the highest amount of fin lift force at that moment.
Yeah, you can get a good estimate for it, just for future reference with like these RAS, especially it'll simulate the AOA with wind gusts. Your highest AOAs are going to move around. So that's a good way to kind of get an upper bound. I think 6 is reasonable. I'm just curious. So, yeah. Other question, your bevel angle on your fins is 41 degrees, like your chamfer, leading, trailing. How come?
Yeah, with the tools we had available, using the CNC mill to get a clean cut rather than try and sand it down ourselves, that was just the drill that we had available. If possible, excuse me, if possible, we would have liked to get a more steeper angle, of course, because that's better for aerodynamics. But that's just what we had available.
Sure. I was just curious. One trick you can do with that, if you're wanting to do more, if you do it on an angle mill, you can mount an angle block. It's what we used to do. So we'll mount like an 8-degree block to the face, and then it makes the fin an 8-degree angle, and then you just have it mill across the face.
Okay. Yeah.
You just have to watch out for chatter when you do the other side because it's super thin. So, but it is an option, something to try in the future. Your fins are aluminum. You talked about that being stronger than fiberglass. Why not carbon?
It's 5 times more. It was like a lot more expensive.
Okay.
I was like,
yeah. It's totally valid. I was curious if that was the answer or if it was to simplify your answer.
No. It was just because it's more expensive.
And then the other question I had was you were doing FEA around your fiberglass airframe tubing. With that being a wound composite, have you done any characterization of the wildman tubing or anything like that?
No. In the FEA, we used steel instead of fiberglass because it had a similar, about, I believe, 200 megapascals for the yielding. So we used that to make sure that the simulation was simplified and ran quicker.
I was curious. It's still fantastic FEA. That is a very hard thing to characterize. I know that all too well. But still, fantastic FEA. So it's a great job on that. And then your safety factor on your rings was 5. Would decreasing that decrease your overall that 1.76, or is there ways to decrease the safety factor there while still maintaining it elsewhere?
I believe I'm forgetting exactly where the minimum safety factor was, but for our rings, we tried to minimize the safety factor as much as possible to optimize mass. But once we tried removing more mass, it started getting into the geometry that we wanted to keep.
Okay. That makes sense. Yeah. Awesome. That's all I have. Great presentation. So
thank you.
Awesome.
Thank you.
Do you have any questions?
I have one question. Like, when we use a machine aluminum, if they bend on landing, so how do you check that it's still pliable? Like it must shift the center of pressure if the fin is bent a bit very far.
Yeah, the way that we would check flatness after a launch is to use I'm forgetting the exact tool name. What you guys use for the
height
definition
gauge?
testing? Yeah, the height gauge. We would mount it on a square and then height gauge it.
We do have like extra replacement fins just in case there is any bending or damage like that. All right.
Thank you. Perfect. Thank you guys very much.
Yeah. That's really slick though. I like it.
Yeah, it came out super cool.
Oh yeah.
What?
That's pretty cool.
And
I like the I like the thrust plate be integrated as well. That's a good solution. So
yeah,
nice work on that.
Thank you very much.
Thanks, guys.
Oh yeah, for sure. Yeah, it's on the table. Yeah. So
So the fins are aluminum.
Yep.
I did like the 41 degrees. First I go, that's cutter.
Yep, exactly.
I was going. That's what he had in the box. That's what.
The reason we use steel for the sim is not because it has the same yield strength, it's because it has the same stiffness. Because that here is
yes, stiffness, not yield strength.
You're good though. That's the only thing.
Did
Everything
you
else
3D
is
print anything before getting into the milling part of it, or just?
We just went for it.
Nowadays, you basically can go for it and have the time.
Yep.
That's all fun.
McMaster with its like next day delivery.
Yeah. They have my credit card.
Same.
Wonderful. What team number?
84.
84. Okay. Are you looking for tomorrow launch or later in the week?
Tomorrow.
Yep.
Yeah.
You passed your safety and everything. Got that all done.
Yep.
And what motor are you running?
An M1350.
Nice. Thank you very much.
Yeah, thanks for coming.
I think this is the first sign that I've seen it that doesn't use fin blankets.
They have a check mark for the no-show.
You guys are here for the podium session for 314, right?
We're not kidding, right? Yeah,
I know, but
yeah,
I'm gonna go yell for them. That's what I'm saying.
Do you know what it is?
What?
The code?
Oh, yeah, I know what the code is.
She just told me 2025.
Oh.
Yeah.
But the team's not here. So.
Right.
Yeah, problem.
That's
we
the
can give
problem.
a presentation. Usually one line. Julia.
Maybe they're in the
It's in
slide.
Oh, yeah. No.
Excuse me.
Using streamlines as a way to decrease your pressure drive. Okay. So as you see, these inlets have been mounted at the very bottom of the rockets. So they are ingesting the free stream inlet. They are going into the free stream is going into those inlets and increasing the weight pressure, which in turn increases the pressure drive. Decreases the pressure drive of the whole rocket.
software called multi-physics ComSol.
I would just read.
And I've been working with that.
I did in 2 hours.
It may just use it differently.
Oh, I'm not.
Various physics calculations.
But I mean, it can go through.
Aluminum steel.
The aluminum was the aft and the steel nozzle. It's like the IREC design.
Okay.
Aluminum nozzle instead of graphite. IREC uses graphite, right?
It's not graphite.
For IREC?
I don't know what that is.
Oh yeah, it was like a top. Like they have their own. Yeah, they have their own formulation for it. Yeah.
I was thinking about it. I don't know. Just don't think about it. Just do.
So what do you think about the first?
We're good. I haven't seen any other grain designs like that.
Yeah, but in terms of like quantitative data, they don't use all that. They use it too, like, because it has really like a better real access if they didn't do like this.
Like deep analysis.
That's hilarious.
Even if they were able to exit a rail, then what happens next? Are they going to hit the maximum altitude if it's
Yeah, well, I guess they didn't mention that during the presentation because part of their idea was that you could tailor it to your thrust curve, and that was a way of controlling altitude.
But the question is it like effective? Like block size like this?
You mean for achieving the altitude?
Yeah.
Yeah, from their tech report, it sounded like that was how they were hitting the altitude more accurately.
But everything was in theory that it really provided.
Other than that they didn't get the altitude before, plus the rail velocity. I worked on a missile back in the 80s, and they had a proprietary grain core, and it was similarly shaped. Yeah.
Yeah, the finishes are good, especially say APCP, but I don't think so. This piece is just giving a more regressive profile.
Why?
Well, it has to change it because you add surface area. Anything with more surface area, you're going to get a faster burn. And a flatter burn, too.
Theirs was regressive. It would have been better if it was more on the neutral side.
If what?
If it's more on the neutral side for the finisher.
Right.
What they achieved is that. Yeah.
Yeah, probably burned really fast and there wasn't much left.
It's 15 minutes late.
The next one waiting.
Yeah, I think that's a team.
That's the team?
Yeah, supposed to be. It's supposed to start right on the.
Are you doing a presentation? No. There wasn't. Josh had several leadership teams. Do you have to interact? Like there's not. I think until like there was a meeting, but they didn't give him stakes. So they were I think it's very
When I changed the judging time, they thought that was the podium time.
Oh.
So now they're waiting on somebody because they're running out of time. They don't have, they weren't ready to make the presentation. They weren't ready. They thought that when I told them 3 o'clock because of our schedule, that their podium schedule was changed.
So you have internet and stuff, so connect to USB, log into whatever.
Can you just give me like a minute? Downloading.
It's okay, I'll get it ready. Yeah, whenever you're ready to start, you've only got 15 minutes now. So you have to move through a little bit quicker.
Okay. Okay. So the team Thrustomati, we're from India. We basically this is the first year that we're going SRAD, 10,000 feet SRAD category. So we have to develop a solid motor for that. So we have designed an innovative solution for sugar motors for the nozzles for that. So we have conducted a multiphysics study before actually manufacturing those components. So we'll be presenting that and as well as showing you the experimental results for what we have done. So yeah. So basically we had some design constraints, which is, yeah. So before starting our motor design, we had some design constraints. The first one was that our propellant had to be KNSB because we cannot use APCP as a propellant in due to regulations prohibiting it in India. So we had to go with KNSB, and other than that, our casing material was restricted to aluminum 6063T6, which has a considerable lower allowable working pressure than 6061T6. So that further limited our ability to push our chamber pressure further. And also our casing outer diameter was also fixed at 101 to reduce our weight. And our total impulse had to be in the N-class band for our rocket to reach 10,000 feet with a CubeSat payload. So considering all these design considerations, our main goal of the motor was to reduce the weight wherever possible. So the problem with conventional nozzles is that they're entirely made up of steel. So for sugar motors, we've previously tested it within past 2-3 years. We've been testing with these nozzles, but as you can see, they're completely made of steel, and that there's a significant mass penalty for this. So if you make it completely out of steel, I think the weight is around like 3 or 4 kgs, and that's a lot of weight that you can save by opting for the alternate design choice that we've made, and that is so we basically have a 6061 retainer, and we have a stainless steel insert going into it. So the one on the left is the retainer, and the insert slides into that. And yeah, so basically the throat is machined into the insert. So the converging part and the throat is contained inside the retainer. The insert, and the retainer consists of the diverging section. So we have ran multiple simulations as to determine the size of the insert and what's the perfect size so as to prevent the retainer from thermally or structurally failing. And we'll be talking about that later on. So yeah, all of these have been machined and manufactured, and yeah, basically it's a slip fit retention because the retainer has a lip and the insert sits on that lip. So we put silicon grease inside the retainer, and then we push in the insert to seal any gases from leaking out. And yeah, that is what we've designed, and we will now tell you how we've simulated all of this designs and validated them.
Hello, I'll talk about some of the simulations behind our nozzle. So when doing CFD, particularly for nozzles, you have to keep in mind that you have very high Mach number and very high pressure gradients, which means that your mesh needs to be extremely fine in certain regions. And another thing that's important here is that we are trying to extract the heat transfer coefficient values from the wall, which means that your heat transfer coefficient values are very sensitive to your mesh quality near the wall and also to divergence issues. So the simulation is on an ANSYS Fluent. And one of the things that I worked on was implementing multi-phase simulations into the CFD. Since we're using KNSB, which has around 40% of its exhaust gases are around liquid and solids, which considerably changes your nozzle characteristics. So when simulating your nozzle, it's important to consider the liquids and solids, which will reduce your specific impulse and characteristic velocity. So the first thing we did was we did simulations to optimize our angles, particularly diverging, converging angles. So it was mainly to do with optimizing mass and impulse. So as you can see, we varied the converging half angles and diverging half angles. And what we found was that we have an optimal diverging half angle of around 18 and converging of around 45. So that's what we implemented in our actual design as well. The actual change is fairly minimal. The angles don't affect the performance as much. Okay, so we use two ways to get heat transfer coefficient. The first one is obviously using CFD to extract the heat transfer coefficient. The other method is to use an empirical formula called Barth's formula. It's here. The Barth's formula, from our experience, is fairly accurate, and it usually overwrites values. So it can be used for most simulations without using CFD, because CFD takes a lot of time and it's prone to errors, whereas Barth's almost always just gives you a reasonable answer. So we used both Barth's and CFD and compared the results. So you can see the heat transfer coefficient around 8,000, which is what we expected, and it aligns with our CFD results. Okay, so we then take the thermal data from CFD or Barth's, and we then implement it into thermal simulation. So it's a transient thermal simulation. It takes the thermal data from the CFD and then time matches it for a burn time. Actually, it's a burn time into 1.5 for FOS. So it's around 5 seconds of total simulation time. And the main use of this is to determine the length of the actual insert, because as you can see, the length of the insert is variable, and it's preferable to have a smaller insert because the stainless steel is a lot heavier. So by using simulations, we can determine the exact length we need, before which the returns become depreciating.
So apart from the safety analysis on our nozzle geometry, we also conducted structure analysis based on the thermal data obtained from safety simulations. You can see over here the static structural equivalent stresses plots across our nozzle section. If you see the stress concentration over the throat is visible in the first figure. So FOS was, we kept a minimum of 1.5 FOS as a limiting factor for ourselves, and that is what was also obtained from simulations. So as was already mentioned, we conducted the thermal simulations were transient, time marched across 5 seconds of total burn time, which is basically 1.5 times the actual burn time of approximately 3 seconds. And based on that transient thermal data, we conducted static structure analysis. A peak one Miser stress of approximately 500 megapascals was observed. After all these simulations, we had to validate our design, which is what resulted in Project Kali being tested on 13th of February earlier this year. So during the static test, we gathered 3 particular data points. First is the thrust data from the load cell. So it's a pancake load cell which gathers the thrust data from it. Then there's the pressure transducer to measure our chamber pressure. And then we used 2 thermocouples. One was kept near the throat of the nozzle, and the other one was on the outer wall of the combustion chamber, that is our motor casing, to get temperature data. These are the temperature plots from the thermocouples. As you can see, we got a peak temperature of 120 degrees Celsius on the outer wall of the casing and 140 degrees near the nozzle throat, which is what was also expected from our simulations, which yielded a result of approximately 150 degrees Celsius. Post-fire inspection was conducted, which showed that the motor hardware suffered minimal damage from the static fire test. Post-test disassembly was particularly simple, where since it's a slip fit mechanism, the nozzle insert and the retainer, the grease that we added to it essentially aided in the disassembly of the entire assembly. We just had to slide it out and it came out. And obviously, since there was no visible cracks and no deviations as such from theoretically predicted performance values, the test was declared as successful. All right, so we're just wrapping up anyways. So to conclude, we started out with our problem statement, that is our constraints, be it limitations of material choices or propellant choices. Based on that, we designed our motor and our nozzle. We conducted thermophysical simulations, and then we validated all of it in static hot fire test. So we've already presented the result for the same. We plan to fly 10K SRAD rocket named Project Varuna with this very motor. So that will be all. Thank you.
Thank you. Did you look at any expansion differentials between the different metals?
We did. So the aluminum expands a lot more than the stainless steel. So post-fire, the aluminum does diverge. Like it does leave a gap, visible gap.
Okay.
Yeah, but the gaps.
No problem.
Yeah, and it's according to a simulation, it's very similar.
There was no exhaust gas impingement on the aluminum itself, so it's not like it directly impinged and damaged the retainer. Plus, there was next to no nozzle throat erosion because the throat ultimately is stainless steel. So that was
right. Okay, very good.
Is there a layer in between the stainless steel insert and the aluminum?
It's silicon grease.
Yeah.
So that's just to seal the. Just one question about build quality judging. Right. You will be there at 3 p.m.? Yeah. That was what I understand. Yeah, okay, there is some miscommunication over there. Right. I'm really sorry for that. It wasn't the podium, it was the judging.
I will put it like laying down. Yeah, put a pencil on there.
Oh, we got so much battery. Don't even worry about it. What's your battery? Okay, cool. So much battery. Sorry?
Nothing.
Okay. Alright. If you want to plug in with the HDMI cord there, when you're ready. Okay, and then I just want you to talk into the mic.
Yeah, do you know how far away you need to be from me?
Like how far it should be from your face?
Yeah.
I don't know. I guess just try and feel it out a little bit. But yeah.
Hello, everyone. Thank you for coming. We are Team 406 from the University of Washington. Our club is the Society for Advanced Rocket Propulsion, or SARP. We have about 106 total members. We have two divisions, liquids and a solids rocket. This is, of course, the climax of our solids rocket program for the year. We are competing in the 10K SRAD category. So today we are going to be presenting our air brakes aerodynamics characterization and testing and how we did that. So we're going to start with our system goals, what we laid out for the year, and a little overview of our system in particular. And then I'll hand it over to Kira to talk about CFD simulation, wind tunnel testing, and our dynamic simulation. Okay, so I am Ty Hatler. I am air brakes testing RE, so that's me. Okay, what are air brakes? Air brakes are a way to precisely control the apogee of a rocket. So using an onboard computer that estimates the current apogee, it will repeatedly make this calculation. A controller will then calculate how much drag we need to induce on the rocket to slow and reach whatever our target apogee is. In this case, it's 10,000 feet. And so our flaps deploy as shown on the screen and slow us down. So why add this system to our rocket? Last year, we overshot our apogee by about 1,000 feet. And so air brakes will allow us to actually hit that 10,000 mark. All right, so in our rocket in particular, our air brakes module is just in front of the fin can. It's as far back on the rocket as possible as to help with aerodynamic stability when the flaps actually deploy. Our mechanism design is a single motor that spins a lead screw, puts a servo plate down, and forces our 4 flaps outward. So 4 flaps that are 4 inches long, they can deploy to a maximum of 45 degrees, and this is all actuated by a single motor as a fail-safe. So if our motor burns out, if the mechanism gets stuck, anything happens, all of the flaps will freeze in the same symmetric orientation as to not impart a moment on the rocket. So that's really important. Okay, so our overall system goals. At the start of the year, we said that we want our air brake system to be able to reduce the apogee overshoot by up to 1,000 feet within 10 seconds of actuation to an accuracy of plus or minus 1% of the target apogee, being 10,000 feet. So in order to meet these goals, we also need the motor to be able to deploy the flaps during flight and the physical deployment mechanism to withstand all expected forces. So in order to validate this, that our design actually works, we need to know how much each degree of flap actuation will affect our apogee. So we need to create a relation between our coefficient of drag and flap angle through a lookup table. That's going to be the purpose of all of our testing. So from all of this, we can also get our how much load will be on the flaps during flight, and if our flaps will just provide enough drag on the rocket to actually meet our goals. So I mentioned we need a coefficient of drag to flap deployment angle lookup table. So what is coefficient of drag, in case you don't know? We have this equation, which relates our drag force to air density, velocity, coefficient of drag, and object reference area. Coefficient of drag is the only one of these variables that we actually have active control over during flight. So our air brakes can deploy to increase or decrease our coefficient of drag. So we have two ways to actually get this lookup table. We have CFD simulation and wind tunnel testing. And by combining them together and averaging them out, we can validate that they are relatively a realistic number and inform our decision on how to program the controller to actively control our 10,000 foot target apogee. Okay, now I will hand it over to Kira for CFD and wind tunnel.
Hello, my name is Kira. I'm the payload testing lead for SARP, and I will be starting by going over the computational fluid dynamics, or CFD simulations, that we ran on our air brakes system. This was prepared by Emerson, who performed the CFD simulations. Our main goal with the CFD simulations was, as Ty mentioned, to obtain a relation between the angle of deflection and coefficient of drag that would inform our controller on board the rocket. So, to go over how exactly CFD works, it's a discretization of a fluid domain into a fine mesh that can be handled numerically. Shown at the bottom here, each of these cells is a single cell in the mesh. For our simulation, we used about 3.5 to 4 million cells. The governing equations are then applied to each cell, so that's your conservation of mass, momentum, energy from, aerodynamics courses, if you remember those. And that essentially says that anything that goes into one cell needs to come out of the cell as well to conserve these governing equations. So the CFD simulation tries to converge to a solution where this is held true and the solution is physically possible. The governing equations are complicated partial differential equations. Those are then simplified to algebraic approximations with Taylor series expansions. So the computer can just solve a system of equations computationally and numerically. We perform CFD simulations for our air brakes at different degrees of deflection, and we'll get into the numerical results later. This is just an overview of how we did CFD. And to also get into why CFD is limited, it's only as accurate as the user setup. So if you don't have a good knowledge of your boundary conditions or your flight conditions, then your CFD is just kind of garbage in, garbage out. It's also trying to solve chaotic physics with numerical methods, which always introduces some uncertainty, so it requires some comparison to real-life data to ensure it's accurate. And it can be very time-consuming to run and difficult to troubleshoot due to the time-consuming nature of CFD. These plots on the right are just showing a good convergence versus a bad convergence. So, as I mentioned with the governing equations, you want to show that everything going into a cell also comes out of that cell so that mass, momentum, and energy are conserved. So this is showing these plots. It's kind of hard to see the scale here, but they're trending downwards towards zero. That's saying the difference between what goes in and what comes out of the cell is trending down to 0. We're getting good convergence there. Here you can see this scale. Some of the governing equations are predicting things coming in that aren't coming out, or things going out that never came in. Therefore, the governing equations are not conserved, and so this is a bad simulation, and there's likely a problem with the boundary conditions, and some some inputs into CFD will need to be changed to get good convergence there. All right, and now I will be going over wind tunnel testing, which was prepared by Chase and Luca on the payload testing team. I will be presenting it. For an introduction, so we have the same goal as we did with CFD, which is obtaining drag data for various flap deflections, so that's CD to angle deflection relation, to create a lookup table for the controller to use as well. This will also be compared to the CFD data that we gathered. If we get the same data from 2 different independent sources, then we have a pretty good feeling that we can trust it. So this is just to give a sense of scale of our model, which is also shown here on the table. Our model is about 2 feet in length, and our true rocket is 10 feet in length. This is due to size restrictions in the wind tunnel we have access to on campus, and this is a picture of it mounted here. So to go over how we're able to do wind tunnel testing on campus, when we deploy the air brakes in flight, we're at about Mach 0.7. Our wind tunnel only reaches Mach 0.16, so much lower. So we decided to try and prioritize Reynolds number matching because we were limited with Mach number matching. In general, getting the best wind tunnel data requires Reynolds number matching between your flow that you'll see in flight and the flow that you'll be testing with. However, we don't have to exactly match the Reynolds number. As long as the Reynolds number of a flow is above the critical Reynolds number, it's called, then we know that we will see turbulent flow. So the critical Reynolds number for a flat plate in flow is 5 times 10 to the 5th, and it's non-dimensional, the Reynolds number. And the Reynolds number we predict in flight impinging, for the flow impinging upon the air brakes, is 1.58 times 10 to the 6th. So this is well over critical Reynolds number. We're well into turbulent flow. And to kind of show a visual, so this bottom line here is coefficient of drag versus Reynolds number. So past the critical Reynolds number, which is marked with the dotted line here, you can see that the coefficient of drag remains relatively constant. So we can say that as long as we're in the turbulent flow regime, we don't have to exactly match the Reynolds number. We can have any Reynolds number in turbulent flow, and we know that we will get similar coefficient of drag data as we would see in flight. So, in summary, we want the flow impinging on the air brakes in our wind tunnel test to be turbulent, as we predict turbulent flow in flight. So, to show how we decided to do that, we chose to dimple the surfaces ahead of the air brakes to ensure that the impinging flow would be turbulent. Typically, you would do a flat plate calculation and use your characteristic length ahead of the air brakes to determine how long you need for the skin friction to transition the flow from laminar to turbulent. Due to size restrictions of the wind tunnel, we wanted to minimize how long the model would be. And after discussions with an aerodynamics professor at UW, we got the advice to dimple the surfaces to kind of trip the flow and force it to go turbulent. And that way, even if our length calculations maybe wouldn't have been correct, we can ensure that we would get turbulent flow with these dimpled surfaces. So, as I mentioned, these dimples allow us to decrease the length of the upper body tube, fitting it better into the wind tunnel. And so we performed tests with both a smooth and a dimpled nose cone. We had a dimpled section just ahead of the air brakes in both models that we tested. The one shown here is the one with the dimpled nose cone. But we wanted to see whether changing the amount of dimpling would have a significant effect on the results, or whether just dimpled at all means great, you got turbulent flow, and that's that. So just highlighting here how we dimpled the surfaces ahead of ahead of the air brakes, excuse me. Behind the air brakes, this part of the fin can was not changed in length so that we could accurately represent the flow coming off the air brakes and impinging upon the fins. So to go over the actual numerical results, we've been talking about how we did all this, but it's like, okay, great, let's see the numbers. Let's see if this actually worked. So we collected drag data from the wind tunnel testing and CFD. We adjusted the flap angle from 0 to 45 degrees in 5-degree increments to essentially create a lookup table that we could either interpolate between or just grab the nearest value in flight. And so this is showing a plot. So this plot above here is at 3 different dynamic pressures. We also changed the dynamic pressures. I'm not highlighting that because we didn't find it had a significant effect on the results. This is with the dimpled nose cone, as I mentioned earlier. So all of these trend pretty well, along with the CFD data as well, which is shown with this dotted line here. You can't see it, which means they're aligned quite well. This bottom plot is with the smooth nose cone. So we see a similar trend where it's closely aligned with the CFD data. There's a little bit of a split here at higher angles, which I don't have an amazing explanation for, but in general, the trend is aligned well enough that we feel comfortable saying that the wind tunnel data validates the CFD data. And so we ended up using an average of both values that we got from wind tunnel and CFD, even though they were pretty similar. But yeah, that's how we ended up using it in the actual air brakes controller. So one interesting trend to note here is this dip in the coefficient of drag with increasing flap angle, which is unexpected. If you're increasing the angle of the flaps, you should be increasing drag. The main explanation that we have for this is that as the flaps deflect, you see a flow separation kind of behind the flaps there, which decreases the skin friction drag right behind. And so one theory that we have is maybe the skin friction drag is high enough when the flaps are closed that it's actually stronger than the pressure drag that's created from the air brakes deflecting. But it is curious behavior. That's one explanation we have, but we're not super sure why we're seeing that data. We saw that trend also in the CFD data as well. There's a dip here, but we did not see that with the dimpled cone. Since also the dimpled cone creates less skin friction drag, that's maybe another reason that skin friction drag may have been the culprit behind that trend, but definitely interesting to note. So to conclude the results part of this presentation, we started with a lot of questions that Ty went over about the design of our air brakes and parameters that we might have wanted to change and test. We collected air brakes drag data from wind tunnel testing and CFD. And now we want to actually use that data. Okay, great. We know how to impart whatever drag we want on the rocket, but how is that actually going to affect our apogee? Because at the end of the day, that's what we want, is to control our apogee. And so finally, I will be going over the dynamic simulation we ran and the controls we actually used for the air brakes. This section was prepared by Prabhav and Raja on our team, and I will be presenting it. Okay, so this is a overview of the dynamics Simulink simulation that we ran in MATLAB. This is what we used for ground testing to iterate on mostly our drag coefficient controller and also to determine whether our coefficient of drag data was giving us reasonable results for apogee and forces in flight. So to kind of break it down into chunks, we'll start with this section here. So this is the dynamics, I guess this whole thing is a dynamic simulation, but this is the part simulating the actual physical dynamics of the rocket. So included here, we have the motor burn profile to get an accurate initial condition. Since the air brakes actuate in the coast phase just after burnout, we get our initial conditions for that coast phase from our motor burn profile. So that's going to be initial position and velocity. And then also the rocket mass profile, since mass will affect the dynamics of the rocket. This goes into our Simulink simulator block, which essentially has the F equals ma ODEs that are governing the motion of our rocket. So from the dynamic simulation, we get the altitude and velocity. Those go through a white Gaussian noise block just to simulate sensor noise that we'll see in flight. And then that gets passed to our air brakes controller down here. So using position and velocity, the drag coefficient controller, we call it, decides what flap deflection to actuate the motors to. We'll go into more detail about how the drag coefficient controller works in the next slide. But for now, basically, position velocity go in, does the magic, and the flap deflection comes out. And then here we have our drag force calculation. And so we use our flap deflection and relate that back to our coefficient of drag through our lookup table that we gathered from the tests that we ran before. This goes into a drag force calculator to determine what actual drag force we're imparting on the rocket, since coefficient of drag doesn't tell us the force directly. So this includes conditions such as the speed and the air density. And then that gets fed back into our actual rocket dynamics here. And this loop essentially continues until the rocket reaches apogee. So we're able to test, through the simulation on the ground, we're able to test our drag coefficient controller and our lookup table in the loop. In true flight, the dynamics simulation that we showed here would be replaced with the actual rocket and sensor data. But the other two parts are the same software that we will use in flight. So the flight software was tested this way. Okay, so getting into the controller calculations. So we have an apogee estimation equation. To give credit where credit's due, Embry Riddle Prescott, their IREC team, came up with this. They developed this apogee estimation equation and were generous enough to let us use it. So we didn't develop it ourselves, but yes. So to estimate the apogee of the rocket on board, the way that the controller works is it wants to close the error between estimated apogee and desired apogee. So we use this equation, which involves the current altitude, so the position, the mass at burnout, which is just a constant, the current velocity of the rocket, and just gravity, which is another constant, and then this kind of mysterious coefficient here, k, which is essentially just related to the coefficient of drag here. So with this equation, we're able to quite simply relate the drag we impart on the rocket to the expected apogee that we should get, and we can back calculate the coefficient of drag we want to get to our target apogee. So this is how we are calculating it on board. This is being calculated at about 100 hertz frequency repeatedly as we close in on our apogee. So to discuss, kind of how we're using this simulation. So we use a dynamic simulation to verify our air brakes design. So that's the physical design with the length of the flaps, the actuation, the deflection speed, the controller design, and other parts of our overall design. So we ran the simulation with our initial design, analyzed the performance against no air brake actuation to see how much of a difference the air brakes actually made. And then we were able to change some portion of the air brakes design in our simulation and kind of continue through this process. So this was able to save us a lot of requiring test flights to be able to test our air brakes. We were able to just use our dynamic simulation, which was great. Okay, so to get into the results we got from the dynamic simulation, using the drag data and the parameters of our current setup of air brakes, which is 4-inch long flaps with about a 6 degree per second actuation speed under load, we predict that our current system can reduce our apogee by about 700 feet, which is below our goal of 1,000 feet that we mentioned earlier. And so kind of looking forward for improvements we want to make to the system. We're wanting to increase our length of the flaps to 6 inches to be able to impart more drag. We also want to increase the maximum deflection angle, as 45 degrees is a strong limiter in how much drag we're able to put on the rocket. And we also want to increase the actuation or deflection speed, as the speed of the motor has also been a significant limiter in how much we're able to decrease the drag in the small window of time we have during the coast phase. So yeah, this is the conclusion of our presentation. Are there any questions? Yeah.
Are your air brakes flush with the outer part of the rocket, or do they replace it?
Yeah. So the question was, are the air brakes flush with the rocket, or do they kind of stick out? So yeah, this is removed from the rocket here, but this coupler just slides into the rocket structure, and so it'll end up being flush just like another airframe. And this is also, the flaps are made out of the same material that our airframe is made out of. So just kind of airframe that moves, basically. Yes. Yeah, question was, is there a reason we went with the rotating flap design instead of the stick-out design? Ty, do you want to answer that? Or
so there were a few factors. When we were designing it initially, instead of, I call it the pedal design, where it sticks out, instead of doing the pedal design, we went with this because we found that you can actually more precisely control your apogee with this. When you're sticking out the pedal, it activates a lot faster, so it's harder to be more precise with it. Also, it takes, with how we wanted to design the mechanism, it's overall it's more stable for the rocket when we do this, essentially. Yeah, that's basically it. It's safer all around. Yeah. ANSYS.
Did you modify your ANSYS simulation based on the results of your wind tunnel testing to try to make it more closely match the real world, or were they both like independent?
Yeah, the question was, did we kind of go back to our CFD simulation after wind tunnel testing to adjust it and see if we could get more accurate results? We got pretty lucky, I would say, and kind of first try got data that matched closely enough, and we called that good. I think in the future, next year, we're hoping to continue air brakes. This is our first year that we've done this system, and so in the future optimizing, I think, yeah, we could probably revisit the CFD simulations and try and make sure, like, okay, are these boundary conditions matching, like, now the wind tunnel setup that we have, and yeah, going into that more in depth. Yeah.
Does the angle of attack have any influence on like the system?
Yeah, the angle of attack of the rocket, I assume? Yeah, okay. So the question is, does the angle of attack of the rocket have influence on the system? Yes, surely it does. The main things that we've considered as potential effects are potential for a moment to be apart on the rocket there. There'd be more drag on one side of the rocket than the other because if the angle of attack of the rocket changes, then same with the flaps. Currently, in our simulations, we aren't considering angle of attack, and we found that we've only done one test flight with air brakes, and it aligned fairly closely to what we were expecting, I believe. But that would be a potential for an extension of the dynamic simulation and something we're hoping to consider in the future. Yeah. Yeah.
When you got the values for your lookup table, did you use just the wind tunnel or CFD data, or did you kind of weigh the values in a certain way? Yeah, how did you get the values for your lookup table from the evaluation?
Yeah, the question is, how did we actually get the values we ended up using in the lookup table? Was it one or the other or some kind of average? So currently we have a non-weighted average, just like at each angle, the wind tunnel data plus CFD divided by 2. In the future, yeah, I don't think our team is super informed on really like, is CFD better? Is wind tunnel testing better? We've discussed with some aero professors, and kind of jury's still out on that one. But yeah, so we don't have, I think, enough information to be like, we should weight one or the other more heavily. But probably in the future, yeah, that's something we can consider. But yeah, right now it's just an average of the 2. Yeah.
Normal distribution, will that have a big effect on how the controller responds?
Sorry, could you? Oh, for the Gaussian noise. Is that our time? Can I answer this question real quick, or?
I don't know what we're supposed to do.
Okay, well, maybe like super sneaky real quick. I'm not totally sure. I didn't personally work very closely with the sensors we used on board. I don't know if, yeah, maybe I can discuss with my team. We might have more information. We can talk after this, but yeah. Yeah, totally. All right. Yeah. Well, that's our time. Thank you guys so much for coming. That's, yeah, what I was thinking. And also, like, there's, yeah. So we'll clear out for the next presentation, but you guys are welcome to follow us to our table, and we'll keep this stuff out and can keep discussing if you guys have questions. Can you take awesome. Oh my gosh, that. Thank you.
So what's our plan now? Teams, or let's see, what's left? New Mexico State and Texas, San Antonio. Okay, I think we can go New Mexico State.
Can we use this computer to run the slides?
Yes.
I also have mine as a backup plan.
side. Excuse me, which is the password? What is the password?
I do not know the answer.
It's 2025.
Thank you. É, eu dei.
Pegou 4 points?
Peguei. Ah, pra comentar. Acho que é isso. Yep. Oi, não, né?
Mas às vezes não tem dessas.
Não, acho que foi. Acho que é só. Foi, mas eu quero botar duplicado. Que aí você consegue ver aqui também.
Como é que passa nesse teclado americano?
Não é aqui?
Ah. Começa nesse aqui. Falta o.
Falta o Ozark.
Ah.
Acho que vai passar não.
Sim. I saw you. We were waiting for Ozark.
Well, he's supposed to be here.
Yeah.
It's up to you if you want to give him a minute.
Esperar o Ozark ou não?
Vamos esperar.
We can give it a couple minutes.
Okay.
To
I
wait
would
for
say
him.
start. Comes in 11:55. Okay, she'll let him in if he comes. When he comes, she'll let him in.
So we start without him? We start without him or we wait?
You can start without him.
Okay.
Ready?
Yeah.
Okay, it started.
Good afternoon, everyone. My name is Gabriela Aragão. I'm the current recovery team manager.
I'm Pablo Moura, the former recovery lead.
We're representing Minerva Rockets, the team 503 from the Federal University of Rio de Janeiro, Brazil, competing for the 10 kh red solid category. So our work concerns the experimental characterization of parachute drag coefficient and reefing performance and wind tunnel tests for sound and rocket recovery. And these are the people involved in the development. Our motivation was to validate previous parachutes, geometries, and fabric that we had been using. So that's why we did it. And our objectives are to conduct scale model testing in a wind tunnel to measure the drag force generated using a load cell, analyze the relationship between drag force and velocity, create an intern database for drag coefficients, varying geometries and fabrics, quantify opening forces during this reefing,
and by that support parachute design and recovery system optimization, right? And always instigate aerospace research.
So first of all, we need to analyze the aerodynamics of the recovery event. In the parachute descent, the airflow separation creates two different pressure zones. Below the canopy, a high pressure zone is generated, which we call the stagnation zone, and above the canopy, a low pressure region, what we call the wake region, is generated. Naturally, the air tends to flow from the higher pressure zone to the lower pressure, which cause instability in the parachute descent. That's why the pressure gradient generates the drag force, and we want to make this the more stable as possible. We also learned that the porosity of the fabric also improves the stability of the rocket of the parachute, as enables airflows through the canopy, making a uniform wake. In the parachute aerodynamic forces, it can be decomposed in lateral force like lift and a parallel force as drag. In an ideal descent, the parachute trajectory is parallel to the airflow, which causes a no-lift event, and this is what we use. This scenario is what we use to dimension the parachute diameter. With equilibrium forces, we balance the drag force with the weight of the rocket, and we get the diameter of the rocket of the parachute from this.
So this was the wind tunnel that we used and some footage from the actual place. It had a wind speed limit of 39 meters per second, a cross-sectional area of 1 meter square, and a suggested blockage area of 20%. We'll explain that later. This was our experimental setup. So there's a tube fixated on the walls of the machine. And here we have the load cell, which is attached to the prototype parachute by a scatchel. We had a little trouble. We had a little trouble traduction it from Portuguese, but it's like a sort of a U-bolt or I-bolt. Say the name again.
Shackle.
Shackle, that's
it
right.
It is space in the middle.
Okay. So for direction, we use the load cell of 200 kilograms with 80 measures per second. And the idea was to measure the traction on the suspension lines of the parachute as a direct response to the drag force. So by measuring it, you're actually measuring the drag force, right? So that's what we did. And then the mechanical load was converted into electrical signal and then transmitted into our data acquisition device right here. For vector analysis, we try to keep the measurement axis more aligned as the parachute axis as possible for acquiring just drag force and any other decompositions of these forces, because we want to characterize the drag coefficient. So that's what we try to do by making it the rotational free here, keeping it a little loose on the tube so it can rotate and adjust the parachute movement.
To calculate the canopy dimensions, we used a maximum diameter based on the wind tunnel section. And for that, we wanted to reduce Bernoulli effect to avoid the formation of the airflow in the boundary of the parachute. For that, we use mathematical theories for blockage effect, which suggested a blockage area of 20% of the wind tunnel section. And with these assumptions, we went to a circular projectile area to calculate the diameter of the parachute. As the fabric is one of our variants in this test, we used two different fabrics: a hybrid nylon with a mass density of 34 grams per meter square, and ripstop nylon with 60 grams per meter square. With this, we use this relation where the real drag coefficient is a fraction of the drag coefficient of the solid geometry of the parachute. For the geometry, we chose this bow, a semi-ellipsoidal one, which is the geometry that we apply in our rockets, and a cruciform one to vary the geometry and its easeability of manufacturing.
For both of the geometries, we also tested reefing configuration because I see some teams here that actually use reefing, so it's mainly employed, and it will in fact be our recovery system model for our current rocket, so that's important. So it actually consists of a single parachute performing both stages of recovery. So different from main and drone, we use a single parachute with a diameter adjustment system, of course. So it's deployed with its diameter constraint to perform the first stage of recovery, and then it full opens to its full diameter for the second stage of recovery, right? And we are interested in this transition, so the small diameter for the bigger diameter, actually the force involved in it. And we call this the disreefing process. And this method specifically that we use is the skirt reefing. So you can see here what we call the reefing rings, and we pass the reefing line through the reefing rings to constrain its diameter. So you can see here a reefed parachute configuration with its diameter constraint and the wind tunnel test.
And to define the wind speed for our test, we firstly attempt to use radial number scale test, but the result of the velocities exceed the wind tunnel capacity. So we went to another strategy to determine the velocity considering a load of 12 kilos, and a limited area. So for each test condition, we take at least 3 points, and at each take, the model was submitted to at least 20 seconds to take reliable data. In general, we conducted 42 tests, and 31 was considered well succeeded. This is some images of our tests. These are two reefed semi-ellipsoidal reefed parachutes with the opening moment being highlighted like this. And this is for the cruciform geometry, also reefed, and the opening moment in the wind tunnel. With this, we outputted these results, which we catch the force generated by the parachute and measured by the load cell, which was a little bit noisy, as you can see. So to address that, we used a moving average with a window of 10% of the values to smooth the force. And in this smoothed force, we determine what we called a stable period, which was a window of 20% of the data where the derivative was nearest to zero, which is because we wanted to catch the average drag coefficient, which is the last graph right here with the dotted red line. With this average drag coefficient, we plotted in a velocity graph, and we did this to analyze the drag coefficient tendency, and we used the standard deviation to calculate the uncertainty of these values, and we fitted the curve using this exponential model right here. So you can see that the asymptote of the drag coefficient in high velocities, which was our goal to analyze the drag coefficient. Also, we plotted the data in a force versus velocities, a squared velocity, because we wanted to find a linear relation between these two values, and we use it the parameters of the drag equation to we use it the parameters of drag equation as the slope of this line. So as I said, we use a linear regression and a least square fitting method to fit this value. But the uncertainty of the strategy was related big, so we did not follow with this method. Instead of this, we plotted the data in a force versus velocity. So the graph is not a line anymore; it's a curve, and we use the same fitting method, the method of least squared, and the uncertainty was extracted from the covariance matrix. We used the same constant from the drag equation to get the slope of the curve. So this was our final result with the values. The first, we varied the geometry and the fabric of each parachute. So we could determine with this method the drag coefficient experimentally, and we used a Horner reference to match these results. Also, we calculate the porosity of each fabric using a reference to the solid geometry.
So heading to the roofing session, we need to clarify some parameters. First, the drag area ratio, which is the relationship between the reefed parachute drag area and the full open parachute drag area, and the reefing ratio, which is the relationship between the diameter of the reefing line circle, that is the reefed diameter, and the nominal parachute diameter, its full open diameter. So when you plot these two into a graph, it originates these curves, which is like a classical on literature, but we wanted to make our own. So we captured our own data. And so for the reefing ratio, we just arbitrated them, which show 0.2, 0.3, and 0.6. And as for the drag area ratio, we tried a different approach. We actually calculated it in function of the drag force by the wind tunnel testers. So that was it. And this originated this graph and these curves which matched literature. So the thing is that you can dimension your reefing parachute by this graph. So starting off the drag equation for both reefed and disreefed conditions and applying the terminal velocity condition in both of them, so equaling them to the weight, you get to this relation here between the velocities and the drag areas. So if you predetermine the terminal velocities, which is what we do, right? You get to the drag area ratio. And getting to the drag area ratio, you can lead to the reefing ratio. And that's how you dimension a reefing parachute. As for the reefing opening force, if you see this graph force versus time, you can see where this happens, where the opening force happens. It's just this abrupt increase right here. That's why we call it shock force sometimes. So it's like stable force, then shock force, and then stable force again. And based on literature, this opening force depends on the stable drag force, opening force coefficient, drag area, dynamic pressure, and opening force reduction factor. We're interested here in the opening force coefficient, so we can calculate our own and compare it to literature, because it's like a constant in literature. So analyzing this relationship right here, it's clearly a linear one, you know. So when you plot the graph by opening force versus stable force, the stable force being this one after the abrupt change. Okay, so let's make it clear. When you plot this graph, the coefficient you want is just the slope of the graph, so it's easier to calculate. And we came to these results for the semi-ellipsoidal and cruciform, so it's 1.4 and 1.04 respectively. Comparing to the reference, which is 1.7, we get to this relative error here. So in conclusions, It was possible to measure the parachute drag and the opening force characteristics through the wind tunnel test, because that's what we wanted at first. The drag force increased proportionally to the square of the velocity, which was what we considered. A linear feeding of the opening force versus stable force enabled the determination of ripping opening force coefficients and its comparison to the literature. And the geometries and fabric porosity presented considerably different results for each parameter. So they really have an influence on the parachute performance.
So this was our first step studying the drag force in a parachute. So we learned a lot with this, and we also learned what we could improve it in future projects, in future works. So we could promote aesthetic stability to the parachute to reduce drag force decomposition, as we saw that the parachute movement inside the wind tunnel is a lot. So we could reduce that. We could also develop an angle measurement system to analyze the lateral force, like lift, that we don't consider in this study. We also learned that the length of the shroud cord affects the drag coefficient. So another thing that we could vary in future tests is apply different shroud cord length to observe the effect of the drag coefficient and the canopy opening. And an actual present thing that we are doing in our current rocket is implementing a load cell on board the rocket in the recovery plate, to measure the parachute forces during flight, with particular emphasis on this ripping opening force that is the system of our current parachute. And with this, we could compare the real data flight method, real flight data with the data that we collected in a controlled environment. This is the reference that we use it in our work. We use basically mostly knuckle to size the parachute dimensions. We use Horner as the reference to the drag coefficient, and mostly Fox and McDonald to the fluid mechanical studies. We would also like to thank our lab partners, our sponsor, and also thank the organization for this opportunity.
Yeah, thank you so much.
So, any questions?
I have a question about the parachutes that you used for your testing. Did you make those, or?
Yes.
Sorry, couldn't come at the beginning of the presentation. The parachutes that you list in this table, two types. These are both in-house. Maybe next slide or both.
Oh, I think he wants to see the geometries.
No, there are two names, parachute names.
He wants to see the
like
semi-spherical and
No.
yes,
Names of the parachute.
Names of the parachute.
Yeah, you plotted the graphs. So there is a plot with the errors. Hyper D and
Oh yeah, that's the fabric. I built in nylon and nylon ripstop.
Okay. This.
Yeah.
yes.
Yeah,
And there is a one page you plotted with the error margin, so these two compared.
Yes,
Yeah,
this one. We compared the values using a hyper nylon parachute and a nylon ripstop parachute.
What's the material of ripstop? Material? I don't know.
Yeah, nylon ripstop is a
Ripstop.
fabric.
Yeah.
So nylon and different types. So I try to understand the exact materials of this.
Yeah,
Both nylons?
both are nylon, but with different granularity specifications.
So maybe it can be a good idea if you add also a data from commercial.
More information about it.
So solutions. For example, you know, fluid chute company.
Mhm.
The fluid chute, there are many options. You can take one at this plot. What is the advantage of your solution compared to fluid chute existing solution?
Okay.
Then we can see their plot and we can compare.
That would be, yeah. What we try to do is to get the the porosity of the parachute in some literature or data sheet from the commercial, but we could find it, so we needed to rely in our results and trust in our process.
For example, in fluid chute, one parachute that I use, there is a CD coefficient of 2.2.
Oh, really?
I don't know which is better. You know? So maybe that.
What material was the parachute?
I don't remember. But it's if you go to the website, they
We'll look into that.
Any other questions?
Based on your results, which shape and material did you end up choosing?
That's a good question. So the ellipsoidal, the ellipsoidal, because the drag coefficient was bigger. I mean, the cruciform was really low. That's not good for deceleration, right? So we stick to the ellipsoidal, which were our previous ones, and hyper-D.
Yeah. We chose the semi-ellipsoidal geometry, as she said, because it has a higher drag coefficient, which is better for a parachute because we wanted to generate more drag. And with a higher drag coefficient, the dimension of the parachute can be lesser, can be smaller.
Because the drag area is what's important. The drag area depends on the area and the drag coefficient.
Yes.
So, yeah.
And based in relation with the fabric, ripstop 60 was a better one with a higher coefficient, a higher drag coefficient. But hyper-D nylon, as it has a smaller granulometry, we can pack this better in the rocket, so we can optimize the lane of the recovery module.
Yeah, and
so
since it has more porosity, then actually, since it has more porosity than the other one, the effects of instabilities that we shown are mitigated.
Is this the drag coefficient in the main size, or do you show drove size as well?
No, this is the results only for the main size. We separate our results like in a main drogue scenario, in a ripping scenario.
And then we calculate like the fully open diameter. And
okay, that means time's up.
Sorry, we're frustrated.
Very nice, thank you.
Thank you.
I just want to say I love your shoes. They're so cute. All Ross for my mom, but I just couldn't. Good job. You did
really good information.
Yes, of course.
It was really good.
Thank you so much.
Yeah, we
Yes, I got
are
your
already
Instagram.
in our table. We are
Perfect. Thank you so much.
Get a call.
I already have a club.
Okay.
Yes, and some stickers.
Thank you. Have a good day.
You too.
No, just log in here and think. What? 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 This isn't like a school. Just log in and like your. What the fuck is Grow?
I get lost in my. I'm not going to do Flutter.
Yeah. Well. What? Yeah, show your passwords. Whatever. No, why are you doing that? This is a random computer.
Make sure you press I trust this device.
Yeah, and click save passwords. Hello? Should I still hold it? Should you still hold it? Yeah. Okay, cool.
You ready? I can start you?
Yep. Hi, I'm Boyan, and I'm here to talk about our spin can for our two-stage. So here's an overview of our team. We're at Rocketry, and we're working on a two-stage 45K this year. COTS, commercial motors. We have SRAD parachutes. We have active controlled canards, and we have our spin can, of course. But let's just jump into it. So, oops. Okay, so why do we need these canards? I'm sure that our control systems lead can tell you more about that.
Hi, I'm Ranveer. I'm the control systems lead from at Rocketry. So the collaboration between aerostructures and control systems, which was a new team, was required essentially because of some very unique aerodynamics that are created by canards. Just for a quick refresher, canards refer to any sort of fins that are towards the front of your aerodynamic body. So ours, they can be static or they can be moving. In our case, they are moving. So an interesting effect that is created by canards is they create these turbulent vortices that can emanate down an aerodynamic body and create forces on static fins, which can essentially result in you undoing the forces, like the action that you want to do. So it's been very clearly understood for decades, actually, even back to the early days of missile design. If you look at the early Sidewinder missiles or things like that, they included things called rollerons, which were essentially a sort of spin can in the sense that they worked to mitigate these turbulent vortices. But if you can also see here in these pictures, these are sort of examples for how these vortices can emanate down and hit the static fins. Now, it doesn't seem as too big of a deal, but the ramifications can be, especially for us, is that these vortices can end up overpowering the actual control authority of the canards. So say, for example, in our case, we're doing roll control. If we're spinning say at a very lazily, 360 degrees per second or something like that. And we are moving the canards to try and mitigate that. The forces created by the canards, the downwash, could potentially cause the canard, the vortices to put an adverse moment on the static fins themselves, and this moment can end up causing you to actually spin even faster, which presents more issues, obviously, because the canards don't work and it's a bit of a waste of time. But beyond that, you can also end up causing potentially structural damage to your rocket from the rocket spinning excessively. So during the early research for us integrating the canards, we came across a lot of research papers that were conducted, especially by the US military, that they'd released, heavily detailing the effects of this both for subsonic and for supersonic flow. And we realized that we would need some sort of way to mitigate these vortices. And after a lot of deliberation and looking at the various different potential solutions, we landed on the spin can. So I'll pass it back over to Boyan to talk a little bit more about why.
So first, there's a couple common solutions. Of course, our spin can, but there's also another option where we use like CFD, just a bunch of computive power, just to figure out exactly how much the canards can deflect and such. But this is very expensive, and you'll see companies like Lockheed Martin, or really anyone who would make these missiles, they would be the ones to do this. You don't see spin cans a lot anymore, but for our purposes, as college students, or just like amateur rocketry fans, the spin can is like the only logical and approachable approach to canards. So I'll talk about our first design. First, design requirements. First, above all else, we needed the fins to be, of course, stable statically, structurally sound, even if they aren't spinning, because in the absolute worst case where they can't be spinning, we can always just somehow fasten it to the body tube. Our next one would be, of course, making a spin, hopefully. That way we can have our canards active and do all the cool projects. Another one is, I mentioned this before, but about previous designs, but I wanted the spin can to be as simple as possible in terms of manufacturing and design and cost as well, because I've realized that a lot of teams, they start a project for canards, but the issue about the spin can, and especially later on, you'll see, the integration of the spin can with a two-stage complicates things. So they end up doing like maybe different projects like air brakes or other active controls. Another thing is, the interstage coupler has to be attached to the booster as well. And you'll see that this is the main issue that comes across this spin can. So first design, it's very similar to a couple designs found online, but the idea is that it's first an oversized spin can. Below it runs a coupler tube, so there won't be any friction or surface area in contact. We'll have this design had two bearing races of airframe tube size, so there wasn't any like custom made parts or anything. It was just cut from an airframe tube. But this design did have a couple issues. For example, for our design, our fins were longer than 12 inches, so no coupler could exist. Like that coupler would have to be custom made. Also, these two bearing races added complexity in terms of aligning them and making sure that the bowls are in contact with each other. And ultimately, it was just not a very feasible project. It wasn't as simple as I wanted to. So moving on, our next design, it was much simpler. So I got rid of one of the bearing races, and instead I would just have the fin can, still oversized, hanging off of the airframe. It would be held aloft, I suppose. It'll be held aloft by a bearing race attached to the fin can, and then another one on the bottom of this airframe piece. And you'll see after separation that that tube will just be gone, and it's almost like 5 inches of just empty space. So really realizing that this design was just too simplistic. It was just it overlooked too many like structural components. So moving on, the third design, it took a lot of ideas from past ones. It was now using just a commercial coupler, and instead had the airframe just rub against the fin can. It was pushed deeper into the fin can. What's next was that the fin can itself was held aloft by an end cap, and that end cap would hold the bearings, and then that would allow it to spin. But again, the 2 bearing races did cause some issues. So ultimately, this final design was the one I chose to do. So first one is that with the oversized fin can, it would have a coupler that would run underneath it again. It would be connected to an airframe piece that, again, tucks underneath it. This coupler, at the end of the coupler, would have an end cap attached, which is just another airframe tube. And to secure that, along with keeping the inner stage inside flush, would have like custom inserts, basically just to allow screws to just to have threads to fasten towards. Right. But the thing is, for this design, we needed a custom coupler, a custom interstage coupler, and this coupler would be the one that this coupler would be a coupler in a sense. So as a result, the thrust transfer would also have to be changed. So for example, the booster thrust transfer would be first transferred through this interstage coupler, and then onto these thrust rings that are moved up 5 inches. Our sustainer thrust transfer, again, also got more complicated. These thrust rings had inner tubes connecting towards the motor itself, and that allowed it to push onto the rest of the airframe. But with the design finalized, we also did some FEA on it. So we tested the rings for both the sustainer and the booster motors, so the N4000 and the O5500 respectively. They were found to be strong enough for it, and with it wasn't anything out of the ordinary. It was, yeah. Okay, and anyways, so this bearing race would also need to be epoxied onto the fin can. To test if the bearing race the bearing epoxy bond would fail. We also did some more FEA, and we found out that it wouldn't. So it's good. And now for the bottom bearing race inserts, we also checked for deformations and whether or not the screws would shear off. But with that being said, here's our references. But here's our test launch. We tested the thrust transfer at test launch. It worked out fine. Worked out perfectly. No sign of deformation anywhere. And unfortunately, the canards could not be activated at the time, so the spin can didn't spin. But I'm hoping that today, or I'm hoping that tomorrow, we can see it spin and launch. Okay. Any questions? Yes.
What was your favorite part of the design process?
I think my favorite part was just about figuring out how to work, figuring out how to work with all these tubes that I couldn't change the dimensions of. I didn't want to like make new tubes or anything. The only custom made tubes I made were just the interstage coupler and the fin can, which were pretty easy in comparative to other designs. But yeah, it was just working my design to work with these like 5-inch tubes or coupler tubes. Yes.
In this slide 13, I think.
13.
Yeah, here you consider aluminum C61, T6. Did you also consider any other material?
There was another aluminum. I don't. I was worried that stainless steel would be too heavy.
Nickel-based M50 maybe.
Yeah.
Stainless steel can be good for the corrosion.
Right.
And the M50 is for the heat resistant. Especially in the rocket, you have vibration and heat. I don't know, just generic question. Did you have some trade-off, calculation?
Mainly for the material, it was primarily cost-based because I wanted to keep the spin cam cheap. And I knew in terms of strength, I could just, at worst, get a thicker ring. But there was another aluminum alloy I was thinking of. I believe it was 7075. That was a lot stronger. But I don't think at the time many Canadian metal supermarkets had that on stock.
The commented is not for preservation, just generic research objectives. Maybe you can do same design, just change the thickness regarding to different materials, then you can compare different FEAs and just an idea.
Okay. Oh, yes.
Did you do any physical testing besides your test flight of the spin rings when you were designing on design?
While we were manufacturing, we did like spin it, and it did spin. I think it was just the conditions at test launch. It was just much colder, and maybe it was the grease that we used that kind of like froze up a bit, or some like dirt got trapped in. But I think that's another reason why the spin can didn't spin at test launch. But we're aware of that now, so we're gonna make sure that the spin can's gonna stay clean.
What was the temperature of this test launch?
It was pretty, yeah.
Freezing.
Yes. Yes. Okay. Any more questions? Okay.
Thank you very much for listening to the presentation.
Thank you. Can you send the presentation email?
Sorry?
Can you email?
Oh, yeah, sure.
I can give you.
You have your email, or
Yeah. I'll just write it down. We have a project for feeding active feeding and canal control. I can also share details.
Okay. Cool.
Very good.
Thanks.
Very nice presentation.
Thank you.
Um,
I just want to check if I find out
Good. This one. I mean, yeah. In my opinion, both have similar technical maturity in their topics.
So you're going to know more about this than I am. Because I'm not an engineer, and I've never done this kind of thing. So I probably learned as much from them about canards and spin can stabilization.
Actually, these both, let's say, subsystems are very crucial for advancement of the rocket. Both spin can or active fin control. This is very advanced for this competition, and also
for undergraduates.
Yes, and also for in-house parachute. It is also I think in their categories, both are similar. But like.
So which awards would you think that they would be?
Which awards?
So there's the technical excellence, and I put them both down under technical excellence, to be honest.
I think.
Or innovation.
Modeling and simulation. The second
first one.
Second one is RINC is a modeling and simulation.
Okay.
They did a modeling. Right? Am I right? They did.
Well, I don't know exactly what they did. They didn't really go into detail about how they came up with their different. They talked about the iterative process, but I don't know why they changed their designs, other than maybe cost or difficulty of manufacture.
Yes.
But as far as
actually, second one also can be innovation because
I couldn't
it's
decide
a novel mechanism actually. I think second one is definitely innovation. First one is technical excellence for sure.
Yes, I put the first one down.
Yes, that's for sure.
And I also put them down for modeling and simulation.
I'm sorry. Are y'all done with sessions in here?
Yes.
Okay. I just want to go ahead and start breaking down.
They had them set the clock. They got done early.
Well, you don't have no more sessions at all for the day, though, right? Anita will take care of that. The clock.
We're just enjoying the clock.
Oh yeah, absolutely. I'll keep the door shut. Keep the sign up. All right, that room is done. They finished early. Oh, good call. Oh crap! I don't have a computer anymore. Can you stop the string, please? My computer's gone. That's number 2. So make sure you stop the right one. Technically, it's like 2 Bravo, I think. But